Hey everyone. Welcome back to day 2 of the PyHC 2022 summer school. Thanks everyone for an awesome day yesterday and to all our speakers from then. Looking forward to the activities of today. So on the agenda for today, you all already know the everyday stuff. First up is PlasmaPy. Nick Murphy will be presenting for that. And then after lunch, we'll hear on SpacePy from John Niehoff and others. Just a quick reminder of some summer school etiquette stuff. Again, code of conduct, be a good person, you've got it. And then for those who are asking questions virtually, please don't put those in the Zoom comment section. Please put those into the proper channel on Slack. So for PlasmaPy, that goes in PlasmaPy and so forth. And if you have any tech issues you run into, make sure to put those in tech questions. And if you're in the room, you have your index cards, so raise a red card if you're struggling, a yellow card if you want the presenter to slow down. And for today, you can raise a green card if you want a mic brought to you to ask a question, which we will have to do if you ask a question for the virtual presenters, or you're free to come up to this mic here if you'd like. So if you have any other questions, feel free to post in general. And just a couple miscellaneous things. If you're ever trying to find an important link, make sure to check that first pinned post in the general channel on Slack. There's a huge list there of everything I can think of to add, so probably there. If you're on Twitter or on any other social media, we created a hashtag to use for the rest of the summer school. So if you feel like posting about it, make sure to include hashtag PyHCSchool22. And then finally, make sure to hold on to your badges and your internet connection info at the end of today and leave your index cards on the table. And that's all I have. So Nick, if you would like to take it away, it's to you.
Sure. Okay, so I will share my screen. All right, so thank you for coming today. It's wonderful to be here for some definition of here. So the first half of today is going to be a tutorial on PlasmaPy. All right, and I wanted to start by introducing myself and give a little bit about my background. So I went to graduate school in astronomy at the University of Wisconsin in Madison. And for my thesis, I ended up simulating a laboratory astrophysics experiment. After that, I went to the Center for Astrophysics in Cambridge, Massachusetts in the US, and as a postdoc, and then got hired on as staff. And I've been there since. And most of my focus there over the last dozen years or so has been on solar physics, but also fundamental plasma science. And for the last 4 or so years, give or take a bit, I've been spending a lot of my time contributing to PlasmaPy and then also advocating for open and reproducible plasma science. I thought I'd also mention some of my pandemic era hobbies, which are singing songs about metadata standardization. They're wonderful. And then also learning how to play late 1980s video game music on the piano back there. I've gotten a little bit better, but not much. And I want to mention a few of the things for getting set up. So like yesterday, it helps to open a HelioCloud environment at this link, which you should have available. If not, hopefully someone can post on Slack. And then the tutorial, I'll show the slide again at the end, is going to be at summerSchool/plasmapy-tutorial/plasmapy-tutorial.ipynb. It's not going to be the one that has -instructor, but this one, the plain one. All right, and as Julie mentioned, please ask questions in the PlasmaPy channel on Slack. I'll try to keep that open and take a look at it for Stuart Mumford's very witty comments during the tutorial. And I posted these slides on PlasmaPy too. All right, so I wanted to say a bit about why PlasmaPy as part of the Python and heliophysics community. And it turns out that the heliosphere is made of plasma, with a few exceptions like the planet we happen to live on. And kind of going even deeper than that, laboratory plasma experiments, so fundamental plasma science experiments, help us to understand heliospheric plasma observation, so plasma processes that are happening in the heliosphere. And then it's also an exchange of knowledge because heliophysics allows us to study in situ plasma processes in regimes that are inaccessible in the laboratory. So if we want to get distribution function measurements, we can do that in space, but that's really difficult to do in the laboratory. And so plasma physics functionality is absolutely necessary for a data and software ecosystem for heliophysics. And I wanted to mention also that another opportunity to build connections between fundamental plasma science and heliophysics. So this slide is showing a call for proposals. This one was for this past January, where people can propose different experiments at the Basic Plasma Science Facility or Wisconsin Plasma Physics Laboratory, or a few other devices, including the D3D tokamak at General Atomics. And you can propose to do experiments on discovery plasma science. So the next solicitation is probably going to be in about 6 months. I don't know this for sure, but you can check the Magnet US website. The links to it is in the slides in the PlasmaPy channel. And kind of bringing this back is a goal of PlasmaPy is to provide the functionality that can be used for cross-disciplinary plasma research. So what is PlasmaPy? The mission of the PlasmaPy project is to grow an open source software ecosystem for plasma research and education. And a software ecosystem is a lot like what we heard about yesterday for AstroPy and SunPy. It's a set of packages that grow together, are developed together, and are used together. And importantly, there is like the developers make sure that the different packages are interoperable with each other. And so PlasmaPy wants to be, we're part of the Python and heliophysics community software ecosystem. And we also want to grow a software ecosystem for fundamental plasma science. And there are a lot of ways to be part of the community. So on Tuesdays, we have our community meeting. On Thursdays, we have virtual office hours. And we also have an Element chat room. And it also really helps to request new features on GitHub. PlasmaPy is a newer package compared to AstroPy and SunPy. And so we're still in the process of developing core features. And if you suggest new features, if you raise issues with feature requests, that those are really helpful and they can give us an idea of where to go in our development roadmap. And of course, you can contribute not just code, but you can also organize and participate in community events like Plasma Hack Week. And Plasma Hack Week is based largely on Astro Hack Week, and it's going to be held in a little over a month, July 11 through 15, 2022. And a Hack Week is essentially a mix of a summer school and a hackathon. We're going to have tutorials on research software engineering, and we're also going to learn how to contribute to an open source project. I want to mention a few of the biggest challenges for PlasmaPy. One of the biggest ones is changing the culture in plasma science. In laboratory plasma science, in fusion energy sciences, there is a pretty limited history of open source, community-driven software development. There are a few projects, but there isn't the history that astronomy and heliophysics have before the start of SunPy and AstroPy. So it's been a big challenge. Another one has been building community. This is largely supporting new contributors, but also making sure that the spaces that we do have are psychologically safe. There are also some technological barriers, and one of the biggest ones is that there's a lack of open laboratory plasma data sets. So in particular, there's no equivalent to the Virtual Solar Observatory for fundamental plasma science. And this is a big barrier to open science, open plasma science. And one of the things that we've been advocating for has been improving the data environment for fundamental plasma science. And one of the things I like to do is to compare it to heliophysics, where we do have the Virtual Solar Observatory. We do have other ways to access space plasma data sets and solar data sets. And talking to plasma scientists, to fusion energy scientists, and say, we're missing out because we don't have as wonderful access to data as in heliophysics. And another big one, which really I spent a lot of time talking about and occasionally singing about, is that there's a lack of open metadata standards. So data sets from different plasma facilities are pretty different. So that makes a big challenge when we want to create software that works across different facilities. So that's another thing that we've been advocating for. I wanted to mention a few of the subpackages, the ones that we're going to talk about today, and then a few others. So the first one is going to be PlasmaPy.particles. And what PlasmaPy.particles includes is functions and then also object-oriented representations of different particles that show up in plasmas. And this is one of the subpackages that I think is going to be most broadly useful for heliophysics and astronomy. Then after that, I'm going to talk about PlasmaPy.formulary, which includes a lot of the formulae for calculating plasma parameters and things like transport coefficients and collision rates. And then last, I'm going to show an example of calculating a two-fluid dispersion relationship with PlasmaPy. And this includes functionality for understanding plasma waves. There are a few additional subpackages that I'm not going to talk about today that much. One is PlasmaPy.analysis, and this includes analysis techniques for data from simulations, experiments, and observations. We have some useful functionality in there, and some which is in the process of being developed, like a null point finder. But a lot of it is more focused on laboratory plasmas at this point. We also have PlasmaPy.diagnostics, and this includes some functionality for Langmuir probe analysis, one of the most common probes in plasmas, and then also things like Thomson scattering and proton radiography, which is a really fascinating diagnostic for high energy density plasmas, where you launch protons through plasma that's exploding after you shot a target with a bunch of lasers. And by sending the protons through and seeing how much their trajectories are deflected, that can give an idea of the magnetic field and electric field structure within the plasma. And this is something which we can't do in heliophysics, but it's one of the coolest diagnostics that I've heard of. And then we have a lot of utilities also. We also have a few subpackages that are under development, and I didn't want to talk about them too much today because some of the implementation, a lot of it still needs to be developed, but we're probably also going to do some refactoring in these subpackages. And in particular for PlasmaPy.simulation, we have a particle tracker in there, which we're planning on refactoring. And we also want to create fundamental classes for setting up and running and analyzing plasma simulations. We also have PlasmaPy.plasma, which includes base classes to represent different plasmas. And this one is largely inspired by SunPy's map class, which we heard about yesterday. And then we're in the process of creating an add-ons subpackage as an entry point for affiliated packages to be put in PlasmaPy's namespace. All right, so for today, I wanted to give a quick review of astropy.units. We use astropy.units really heavily in PlasmaPy, and so if anyone wasn't here yesterday, wanted to make sure that we covered the essentials so that you can follow along with the rest of the tutorial. Then talk about PlasmaPy.particles, and in particular, probably spending maybe close to half of the time on this subpackage because of how broadly useful it is. And then spend some time diving into different parts of PlasmaPy.formulary, including calculating plasma beta in the solar atmosphere, Coulomb logarithms, thermal speeds, distribution functions, magnetostatics, things like that. Then I wanted to talk about to pretty much show an example of calculating and plotting a dispersion relationship in PlasmaPy. And then I haven't timed this full tutorial, so there's a chance that I won't finish. There's a chance I'll finish early. And if we do finish early, then I'll cover some tips on writing clean scientific software for the last small number of minutes. And if not, I'll share the slides to that in the PlasmaPy channel after this. All right, so I wanted to put this slide up again. So please open an environment if you haven't done so already. And then I'll show the location of the tutorial. And again, please ask questions in the PlasmaPy channel on Slack, which I'll try to monitor. And also check Slack for these slides. So with that, I will pull up the tutorial. So if you go to the summer school directory and then PlasmaPy tutorial, then you can go to plasmapytutorial.ipynb, so not the one that is -instructor. And so we can open that. And then hide that. So as I mentioned, this tutorial is going to cover a bit about astropy.units, PlasmaPy.particles, PlasmaPy.formulary, and PlasmaPy.dispersion. So the first thing we want to do is a whole bunch of imports, which we can get out of the way. So press Shift Enter to execute the cell. And that should take care of everything, though I did include the imports in the individual sections. So let's talk about astropy.units. So I won't go in as much depth as we did yesterday, but we usually import astropy.units as U. And we can create a physical quantity by taking a number like 60 and then multiplying it by u.km. And that'll give us a quantity with that represents 60 kilometers. And this is something that you can do with NumPy arrays also. We can also create a quantity with compound units. So V equals 88 times u.imperial.mile, and then print V. And that'll give us 88 miles per hour for those of us who are Back to the Future fans. Operations between quantity units handle conversions automatically. So we can do something like 1 times u.m and add that to 25 times u.cm, and that will give 1.5 25 meters. So we don't have to do this manually, which is, I find it magical. It's one of my favorite things about the Python ecosystem. And these operations also get handled automatically during multiplication or during different operations, multiplication, division, and exponentiation. So we can do 2 times u dot m, and then we can cube it to get a volume. And those unit conversions are handled. So there's one question about the formatting of my output doesn't match what's on screen. One thing I noticed yesterday is that sometimes it can take a little bit of time for the formatting to get formatted. So as Russell said, it sorted itself out. So be just a minute. Okay. So the next thing is that if we take a quantity, so we define the velocity above, and we can use the .to method to convert it to meters per second. And then we can get, wait a second. All right, I got an error. And okay, so it says that length, miles, and meters per second are not convertible. So this means that I probably did an error above. So that's miles per hour. All right. One thing I've learned after 10 years of experience is that error messages are more useful if you actually read them. All right, so I redid this. Velocity equals 88 miles per hour. And then I can redo this, shift enter again, and get that it's about 39 meters per second. And we can also do this with the unit operations themselves. So, or with unit objects themselves. So v dot to, and then u dot km divided by u dot hour. And we can convert the velocity, find out that it's 142 kilometers per hour. So pretty fast. All right. The next thing is that for some reason, which I have opinions about, plasma scientists often use the electron volt as a unit of temperature. And this is a shortcut, which is essentially the thermal energy per particle. So if we take the temperature and multiply it by the Boltzmann constant, we can get an energy and convert that to electron volts. And that ends up being a proxy for temperature. But it's a unit of energy, not temperature. So by default, we can't convert electron volts to Kelvin. But we can make use of equivalencies, as we talked about yesterday. 1 times u dot ev dot 2, and we can do Kelvin, K as a string, and then set equivalencies equals u dot temperature underscore energy, call that, and then shift enter, and we get that 1 electron volt corresponds to 11604.5 Kelvin, which is a useful thing to remember if you're like me and you go back and forth between fields. And the last thing I wanted to mention is that there's also astropy.constants, so we can import astropy.constants as const, shift enter, and then get the speed of light as const.c, so about 3 times 10 to the 8 meters per second. All right, so that should be enough to cover what you need to know for using PlasmaPy. All right, so let's move on to PlasmaPy.particles. And we already imported it above, but we can import it again. And the first thing we can do is use some of the functions that can get information about different particles that might be present in a plasma. And the input of these functions is a representation of a particle. And for instance, we could get the atomic number of Fe, iron, and shift enter and find that it is 26. We can also provide a number that will get interpreted as the atomic number. We can do that as element name and then do 26 and shift enter and get back that it corresponds to iron. We can also use standard symbols for the names of different particles. So we can find out if use is stable of, in quotes, E minus to find out if an electron is stable, and it is. And we can also find the charge number of a proton and get that it is +1, where the charge number is also sometimes known as the integer charge. Okay. And there are also, we can also use some of the Unicode symbols for different particles also. So we can get the particle mass. And then if we type /alpha or another Greek letter, and then press tab, it will get converted to the appropriate Unicode character. And so just notice that we need to put that into a string. And so if we want to create an alpha particle, one of the ways we can do that is through this, which can sometimes make code a little bit more readable.
Sorry, I have a question. How do you list all the available constants when you import them? Like when you do import astropy.constant. Just print const or what?
So if we wanted to do that, I'm going to click on this and press B to create a new cell. We can do dir const and then shift enter, and that will give all of the constants.
Okay, thanks.
Okay. Excuse me. All right. Got a comment too fast, so I will attempt to slow down. All right. That is really helpful to know since I have a tendency to go fast. All right. We can also represent isotopes with the atomic symbol followed by a hyphen and the mass number. And so we can use the half-life function to get the half-life of our favorite radioactive particle in seconds. And that is half_life, and then in parentheses, quotes C-14, end quote. So the half-life of carbon-14 is 1.8 times 10 to the 11 seconds. And since that's not so useful an output, I'm going to do 2 YR and get that it's 5,730 years. We can also represent an ion by putting in a string together with charge information. And so we can do that with charge number of, let's say, Fe-56, and then do 13 plus. And in this, we have 56 as the mass number of iron, the number of protons plus neutrons, and then 13, which is the charge number, and plus to make sure that it is positive. And then we can press Shift Enter again and get the information right back that the charge number of this ion is 13. We can also get the, so PlasmaPy is pretty flexible in terms of the inputs that it accepts for particles functions. So we can also do something like particle underscore mass, and then do iron dash 56, and then do plus 13. So if any of us happen to forget that, or whether the plus sign should go before or after the charge number, the ion charge, it can do either. So we do shift enter again, and we can get the particle mass, which takes the mass of iron 56 and then removes the mass of 13 electrons. And we can also do something like particle mass, and then do quote iron dash 56, and then no space, plus 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 plus. I think I got that right. And it'll give you the same amount. So I did get the number of plus signs right. And this isn't so helpful for, or readable for, high charge numbers, but if you wanted to get singly ionized helium, this is a nicer, more compact notation. All right. It's also possible to provide most of these functions with another keyword argument, Z, which represents the charge number of an ion, and mass num, which represents the mass number of an isotope. So we can do particle underscore mass, and then Fe, which will give the element. You can alternatively do an isotope there. And then Z equals 13. So the same ion as above. And then mass underscore num equals 56. And then shift enter, and we get the same number again. So this is another way of representing the same ion. So up until now, we've used a lot of functions to represent or to access different particle data, especially for the periodic table. But we can also create particle objects. How's my, please let me know if the speed is too fast still. All right, so we can create a couple of objects, and let's create a proton. And for that, we will use the particle class to create a particle of using the same symbols as above. So in this case, using a string containing P plus to represent a proton. And we can also create an electron as particle, and then in quotes, electron. So the full name of the particle. And then to use the last example as above, we can do, oh, yep, notice in the Zoom chat, electron, thank you. This is one of the example of how code review can be really helpful. So I do appreciate that. All right. So we can do iron 56, nuclide as particle, and then do Fe, and then Z equals 26, and then mass num equals 56. So not quite the same particle as above. And we can press Shift Enter to create the proton, electron, and iron 56 nuclide objects. Or nuclide is another term for nucleus. All right, so now that we've created those, we can access different particle attributes. So if we want proton.mass, we can get that. If we want to do electron.charge, we can do that also. And also we can get electron.charge underscore number, and that will give us -1. And then for the last one, we can get iron 56 nuclide dot binding underscore energy and get the binding energy. And in this case, we can convert it to, let's try GeV. And Shift Enter, and we get that the binding energy of an iron 56 nuclide is about half a giga-electron volt. One design decision that we made for PlasmaPy was to use SI units throughout the package. And part of this, the main reason is that SI units are the emerging standard, and because plasma physics is so interdisciplinary, it can be really helpful to go along with the international standard. Okay. We can also, for fundamental particles, get the antiparticle, and we do that with the antiparticle attribute. So we type electron dot antiparticle and press Shift Enter. We can get a positron, so E+. And we can also use the tilde operator, if I can find it on the keyboard. So tilde of a proton and Shift Enter, it'll give you an antiproton. And this is actually a really fun thing to implement. One of the co-development practices that we've really made good use of in PlasmaPy is procrastination-driven development. So if you have another project which you're supposed to be working on, and something that you want to be working on, you can be really productive on the one that you're not supposed to be working on at the moment. So I highly recommend it. I think PlasmaPy probably started as a procrastination-driven development project. All right. The next thing is ionization and recombination. So there are two methods on each particle object, which are recombine and ionize. Let's create a deuterium. Deuterium equals particle, and then we can do D0, oops, 0 plus. And actually I need to finish that, quotes, and do this. So if we do this, then we can also get deuterium dot ionize, and then parentheses, so we call it, and get a deuteron, so a deuterium nucleus. We can also do this with by providing these with a number. So let's do alpha equals particle of alpha, in quotes. And then alpha dot recombine. And then as an argument, we provide 2. And then shift enter. And we get a neutral helium-4 atom. So we can take a different number of electrons to recombine or to ionize. As it stands, when we do it like this, we're not changing the charge number of alpha itself, but creating a new particle. And so we can do this again with argon. So we can say argon equals particle of AR 0 plus. And then argon dot ionize, and then set in place equals true. And then we can print argon. So we create a neutral argon atom, ionize it, remove 1 electron, and then we print it. And we find that argon was changed in place to argon 1 plus. All right, and there was a question in the chat about can we have something like electron dot mass rest to get the electron rest mass? And so the you can use the mass energy method or attribute to get that. The rest mass is the mass that's given in that. One feature of PlasmaPy that we're working on, didn't get it done quite in time for this, is to create a relativistic body class. So that's a body where you can take a particle, or a class where you can take a particle and set it at a particular velocity, and then get the momentum, Lorentz number, energy, velocity, fraction of the speed of light, and things like that. And that will probably be in the next release of PlasmaPy, but not there yet. All right. So thus far, we talked about particles that actually exist. So things that are on the periodic table or are fundamental particles. But there are times where we want to create a custom particle. So something like a dust grain, or if we're doing a simulation, could do that also. All right. And for that, we can use the custom particle class. And so let's say CP, short for custom particle, is custom particle, and in parentheses, let's say 9e minus 26 times u dot kilogram. So we set the mass. And then 2.18 e minus 18 times u dot c. So you can get the set the charge here in coulombs. And then you can optionally define a symbol also, which is, so we can say that this is Fe 13.6 plus. And so with this command, we can create this custom particle. And custom particles behave a lot in the same way as a regular particle. So we can get cp.mass, shift enter, cp.charge, shift enter, and then cp.symbol, and shift enter. So custom particles can be used to represent things like average charge states, for example.
Hey, Nick. Question in the chat. What about negatively ionizing a particle?
Oh, yes, we can do that also. So I'll go back up here. And let's say argon dot, oh, you mean, so do you mean, can you use a negative number for the ionize method? Or creating a particle that is negatively charged, and that should work. Yes, so you can use the recombine method to add additional electrons and get a negatively charged ion. And I think, let's see if I remember correctly, if we do 10, oh wait, no, I set warnings filter off. So if you get an argon atom, then let's see, then often it'll give a warning saying that, do you really mean that? Because a 9 times negative ion will not happen often in nature. And so the next question in the chat is using plus equals to get a, so argon plus equals particle of electron minus. And we don't have it set up so that you can use the plus equals operator to do the ionization and recombination. So that functionality we use to create a particle list instead. Okay. And I'll get to particle lists in a little bit. All right. So for this part, one thing to note is that if we set something to, if we forget to set the mass or charge, it will get set to numpy.nan, so not a number in the appropriate units. So we can do custom particle and then parentheses 9e minus 26 times u dot kg, and then press dot charge and shift enter, and we get that it is the charge is not a number, coulombs. All right, so one thing I wanted to note is that we aren't yet able to use custom particles in a lot of the functions in PlasmaPy.formulary, but we're in the process of adding the architecture for that. So some of that work will be done by PlasmaPy 0.8, and we're hoping that it will be complete or close to complete by 0.9. The next question is it possible? Right. Is it possible to generate a superparticle like the ones used in particle and cell models? So we don't have functionality to like create a compound particle yet, but you can set something up using custom particles to do something like this. So, but we don't have the functionality yet to create a superparticle. And so the next thing in the chat, since plasma is usually an electron ripped out from the proton, so we're not using negative ionization in PlasmaPy. there are occasionally negatively charged particles in plasma. So this could happen in cold plasmas in the laboratory. And also there's a very small amount of H- in the photosphere, which ends up being important for opacity. So there are occasions where the negatively charged ions do show up in a plasma, but yeah, they're not very frequent for the plasmas that we tend to care about in heliophysics. All right. The next thing, which I want to cover, is particle lists. And oh yeah, before you, yes, please do keep asking questions in the chat. I think it's pretty helpful. I'm going to try to answer them at the ends of sections, since that's a natural time to do that. Okay, so we created a particle list as a container for particle and custom particle objects. So let's create a particle list with iron ions equals particle list, and then in parentheses, we can create another list or tuple, and then have different representations of particles. So we can do Fe 12 plus, then Fe 13 plus, and then finally Fe 14 plus. And then in the list, and in parentheses, and shift enter to execute it. And it's important to put in a bracket or parentheses here. So you need something that is a list or collection, an order list or collection, in order to create a particle list from it. The nice thing about a particle list is that you can get the different attributes of multiple particles at once as an array. So if we do iron ions dot mass, we can get an array containing the masses, which are 1 electron mass each. We can do iron ions dot charge, and then get different multiples of the elementary charge. And we can do iron ions dot symbols, and then shift enter, and that will give us the different symbols that we had for it. So the question is, why does it take iron 13 plus but not Fe space 13 plus but not Fe 13 plus without a space? I think that was I think the big reason is to avoid confusion with the mass number. So if we do something like, let's see, oops, didn't need to do that. Okay. My microphone is like blocking my view of the keyboard, so you're getting an extra number of typos. So if we do iron dash 56 and then 13 plus, then it ends up running together. So I think that's why we made the design decision to have a space in between. Though in some cases it can end up, oh yeah, and also if we do minus 13 instead of 13 minus, then it would also be a little bit ambiguous. So it's to reduce the chance of ambiguity to have the space in there. But yeah, that is a good question. All right. So we can also create a particle list by adding particle or custom particle objects together. So we can do proton plus electron, and then get a particle list with a proton and an electron in it. And we can also use a lot of the list operations on this also, which I won't go into. And we can also get an average particle. So if we do iron ions dot average underscore particle, and then call that, we can get a custom particle from that. All right. Okay. Or let me know if there's anything in the chat that's above what's at the bottom. I haven't followed that completely yet. Okay. Another thing which we sometimes need to do is to figure out if a particle is in a particular category or not. So something like a lepton or baryon or ion. So if we take, if we define a muon as muon equals particle, and then in quotes muon, and then do muon dot categories, then we can get a set which contains the different categories that a muon belongs to. Okay. And the particle also has another method, which is category. And we can say something like, is a muon a lepton? And we get the answer is yes. Sometimes we want to use more complicated conditions. And so we have a few other keywords that we can use. So let's say electron dot is category. And then let's put this on multiple lines to make it a little bit more readable. So we can set the require keyword to be lepton. Oops. The exclude keyword to be baryon. And then the any of keyword to be, in a set, boson or fermion. All right. And press Shift Enter. And what it's doing here is making sure that electron is a lepton. It has to be a lepton. The particle cannot be a baryon, which an electron isn't. And then it has to be at least one of boson or fermion. And it is a fermion. So we're good there. All right. And because the electron met all those categories, it returned true. One thing which is helpful is if you want to see all of the categories, we can do, let's see, we can print electron.is category, and then dot again, valid categories. If we do this, then we'll get all the different categories that are possible among all particles. So this isn't specific to electron, but it shows all of the, so if we can do things for like neutrinos or baryons or whatever else. And one thing I noticed when doing this, putting this tutorial together is that we didn't add particle list.is category for the 0.7 release, the current release, but we do have it added for the 0.8 release. So our 0.8 release is due approximately 1 month ago. So hopefully you'll be able to get to it soon. It probably actually will happen in hopefully the next few weeks. All right. So next we can go on to dimensionless particles. And occasionally in simulations, we end up using a dimensionless particle. So we can normalize the simulation quantities to have like a dimensionless mass, dimensionless charge, and so on. And for situations like that, we have a dimensionless particle. So let's create one of those. So dp dimensionless particle equals dimensionless particle. And then we can say the mass equals 0.000545. And then the charge equals -1. And in this case, we can press Shift Enter, and then we can get the properties in pretty much the same way as for custom particles and regular particles and particle classes. So dp.mass, and we get 0.000545. And then dimension or dp.charge to get -1. And in this case, I think what I was thinking is putting together a dimensionless electron. And one thing to note is that because a dimensionless particle does not uniquely describe a physical particle, it can't be contained in a particle list, and it won't be able to be used in formulary functions. So there's another question in the chat. Is there a reason why a muon isn't already a particle object like an electron? So one thing that we can do is from PlasmaPy.particles import proton, electron, and things like probably alpha, then probably deuteron, also deuterium plus ion. But we can't do things like so these particles are already pre-constructed because they end up being needed pretty often. Though I didn't use that before since these are also good to use in examples. But we can't do from PlasmaPy.particles import muon, probably. So we got an import error for that. And the reason why is that we decided only to use the most commonly used particles in plasmas to not have our namespace too crowded up. Though if there is a strong demand for it among the community, we could expand this list. But otherwise we can use the particle class as a constructor. The next question is, what would be an application for using a dimensionless particle? That is a really good question. The one that I usually go to is if we want to do a particle in cell simulation, usually the quantities in that get normalized to different plasma timescales and different plasma other things, lengths, and so on. And because the simulation parameters get normalized, they end up being dimensionless. So that is one place where a dimensionless particle can be used. And next question is, can you please go over the syntax to create a dimensionless particle again? And so that is here. So we can do dimensionless particle, then have the mass keyword equals this, some number, and then the charge keyword be another number. If I remember correctly, these keywords are keyword only, because if you do, let's see, dimensionless particle, press tab complete there, then do 1, 2, when reading it, we don't know if it's going to be a mass or a charge there. So we need these as keywords in order to keep this as readable. All right. So I'll delete that. And yeah, for situations where if you have a function where there are multiple arguments that have the same units, it ends up being really helpful to make sure that these keywords end up being keyword only, so that you have to say what it is, because otherwise you can end up having mistakes and things like that. All right. And I think those are wait, there's one response. Just to follow up, it does seem to be defined in the particle class though. That's why it had information already by giving it the name muon. Right, so we have a pretty broad range of particles that we can include, or that we can create from the particle class. And there's only a couple of those that are predefined for convenience. Let's see, so we can do things like for a tau neutrino, for example. One open issue in PlasmaPy is to create a list of the available particles and particle aliases and generate that for the documentation. We probably won't have that by the 0.8 release though, but that is something which would be really helpful. And that also is emulating what AstroPy does for units and I believe constants also. But if you like updating documentation and are looking for a good first contribution, that's one that you can look for. All right. The next thing is nuclear reactions. And to do that, we can use the greater than operator. So let's define a few particles again. Deuteron equals particle of D+. For some reason, I always put my mouse like right over where I'm typing. So deuteron equals particle D+. Triton equals particle of T+. Alpha equals particle of, and then let's use that trick again, or you can type a slash alpha or backslash, I can never remember. And then press tab and it will create the Unicode character. And then neutron equals particle of n, lowercase n. And I should mention that a lot of these aliases are case sensitive because capital N would be nitrogen, though things like the full names are generally not case sensitive. So you can press Shift Enter to execute it. And now let's try out something that I believe was originally suggested by Stuart Mumford approximately 4 years ago, which is energy equals deuteron plus triton, and then the greater than symbol, alpha plus proton. And so this is the, oh wait, no, I had this wrong. Neutron. so alpha plus neutron. This is the nuclear reaction that is being targeted for nuclear fusion power. So you can kind of tell that I originally wrote this example for a fusion audience. Otherwise, I would have chosen one of the reactions in the, I guess, what is it? The proton-proton chain or CNO cycle. But can't remember those offhand. So we can get the energy. And then let's do energy dot 2 and then MeV, so mega electron volts. And then shift enter again. And we get a number which is pretty recognizable to fusion energy scientists, which is 17.6 mega electron volts. And now that we do have that, I'm sorry, we can also put in an invalid nuclear reaction. So let's try a deuterium nucleus, plus a triton, tritium nucleus, and then greater than sign, alpha plus 3 times neutron. And since this is not a valid reaction, we get an exception, a particle error. And if we scroll down to read the error message, we get that the baryon number is not conserved for reactants equals a deuteron plus a triton and products equals an alpha particle plus 3 neutrons. So you can get an additional check in this to make sure that everything is going okay. One possible direction that we might go in for PlasmaPy is to have an operation like this, deuteron plus triton greater than sign alpha plus neutron. Instead of having that return an energy, we'd like to have that return a nuclear reaction class instance. So to create an object that represents a nuclear reaction, and then we get nuclear reaction dot energy to get the energy from that. But we could also potentially put in attributes like the cross section, which for a few reactions is particularly important for like fusion energy scientists. So there's a chance that this functionality will change in the future and become more awesome. This was another thing that was really fun to implement. Let's see, so I want to cover one section and then I think we can go to the break probably. And that is having particles as function arguments. So it's pretty often the case that we'll want to write a function that takes one or more particles as an argument. And to do that, we've created the particle input decorator. And this thing is like pretty useful. So let's write a function where we demonstrate this. So let's say ampersand, or no, the at symbol, whatever it's called, particle input, and then define a function f, and then let's create an argument for that and annotate it with particle. And then let's return the argument. So we return particle. And then shift enter. So let's see what happens when we pass this function a representation of a particle. So F of a string for a proton, and we get a particle object representing a proton. What this decorator does is take arguments that are annotated with particle and convert those to a particle object. And this makes it a lot more straightforward to create these functions, because there's a lot of repeated code that you could end up with for doing this. And you don't want to repeat that in functions themselves. All right. So let's see. The next thing is that we can use the, oh yeah, so we can also try this on a particle object. So F of particle P plus, and then it will take the particle object and pass it through as expected. So it works fine that way too. All right. So the next thing is that we can use the same keywords for is category and use them in particle input also. So let's say at particle input, and then require equals lepton. And then we can define a new function, g, and then have it be particle colon particle to annotate it with the particle class, capitalized, and colon again. And then let's say let's just pass it because we don't need it. Okay, so now that we created that function, we can pass G an electron representation. So we have a require equals lepton, and we pass it a lepton, and it goes through fine. So in this function, particle was transformed into an electron particle object. But if we do this again for P plus for a proton, then we get a particle error. And if we scroll down, it says that the particle P plus does not meet the required classification criteria to be a valid input to our function, which is G, and that the particle must belong to all of the following categories, which includes lepton. So if we're creating a function like atomic number, and we want to make sure that only elements get provided that function, then we can use the particle input decorator with the require any of and exclude categories in particle input to do that, to take care of these checks for us. Now there's one more thing that we can do, which is if there are parameters to a function named element, isotope, or ion, then particle input will check to make sure that that particle does meet that criteria, that it is an element, isotope, or ion. And so let's try that out. So we can do particle input and then def, let's call function y of ion, and then annotate it with particle, and then return ion, and then shift enter, and we can redefine that. And let's pass it an ion. So how about Fe-56 8+, and shift enter, and it went through fine. But if we do call this function y on an electron, then we get an invalid ion error. And it says that the argument ion equals e minus 2y, our function, does not correspond to a valid ion. And so this ends up being a shortcut to take care of additional handling also. There's a question in the chat. What's the syntax for multiple categories in require? Let's scroll up. That is a good question. And that would be a set or a list. And I usually do it as a set because the order doesn't matter. So you can say require lepton or and fermion. And then shift enter again. And then if we do this again, it will create the same it'll have the same result because it meets both categories. Yeah, that's a good question. You can do this for arbitrary categorization also. There's another question. Could you define a function that takes 2 ion arguments? The short answer is that's not something that would be handled by particle input. In practice, it hasn't ended up coming up too often for our functionality. So we ended up not implementing that in order to keep the implementation of particle input to be not too complex. But yeah, that is something that could be done using particle.is category inside of a function. All right, and then a follow-up. If I do require equals category 1 and category 2, we have a and logic argument, or is there or? Yes, so the any of, scroll up. We could do any of equals, if I spell it correctly. Let's say baryon or boson. Having a hard time remembering categories. So you can use the any of for or, and it'll have to meet this condition, the require condition, as well as the any of condition. And then we can do exclude equals ion. All right. Are there any other questions before we break? Will this lecture cover functionalities for magnetized plasma, such as those in the ionosphere and magnetosphere? In the formulary section, which is coming right after this, we're going to look at some examples for the solar atmosphere and for Earth's magnetosphere. So yes, please come back in a few minutes. Oh, nice, Evelina. Yes, we've gotten pretty far. We still have a long way to go, so there's a lot of development ahead of us. And we're happy to invite new contributors. All right. There's one question potentially coming in the chat. Okay, are there any questions from the audience? I think there might be a microphone that is set up somewhere, or that could be handed around. So.
It looks like we have no questions currently.
Okay. Cool. In that case, let's take a 17-minute break. So let's come back at 15 minutes after whatever hour it is there. And we'll go over
4:15. 4:15.
We'll go over ionization state data structures, and then formulary stuff. And I'm getting less into this as I thought I would. So I might not be able to get to PlasmaPy.dispersion, but dispersion relationships confuse me, so it's fine. All right, see you in 17 minutes.
Awesome. Thanks, next season.
All right, I can probably start momentarily. Okay, are we set?
Go ahead, Nick.
Okay, cool. Breaks are important, so it's important to take them to their fullest, and then a few minutes after that as well. I wanted to.
Hello, hello, hello.
Hi.
And the other, all right, whatever you did, work there. And the other one?
Okay.
The other one is not, it's on.
Hello, 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 hello.
Hi. Thank you. Okay. Cool. I shall get started then.
Yep.
Okay. I'm not completely sure what's going on there, but I'll assume that everything is under control. I wanted to show briefly PlasmaPy's pull requests page because there are a few pull requests of notebooks that are currently underway that happen to be the notebooks that we're going to cover shortly. So if you do have suggestions on how to improve this, they would be much appreciated since they're not quite yet in PlasmaPy's documentation, but will be soon, unless I decide to take a vacation for 10 weeks starting in about an hour and a half, which might happen. Probably not though. But all right. So there was one thing I was going to mention. So right now, for particle input, the annotation is particle. And one thing that we're going to be doing in the near future is enabling it to be particle-like, which is for improved typing. This one, if you use like static type checkers, then it's important to have this taken care of. But we plan on having the particle annotation still sticking around for a while. All right. The next thing that we're going to cover is the topic of ionization state data structures, which are one of my favorites for PlasmaPy and heliophysics also. When I say ionization state, what I mean is that it's the fraction of ions or ionic levels that are for the element. So to say it a bit less confusingly, the ionization state distribution of helium might be 10% helium 0 plus, neutral helium, 70% helium 1 plus, and 20% helium 2 plus. And the reason why this is important for space science is that when we observe these ionization state distributions at, for example, 1 AU, we can get a lot of information about what the plasma was like at a few solar radii away from the sun and what its temperature history was, because these ionization states essentially freeze out. So ionization and recombination mostly stop after a few solar radii away from the sun in the solar wind. So between 5 to 10 solar radii and 1 AU, there isn't much ionization or recombination happening. So it's a really powerful diagnostic. And I'm going to go into the data structures for recording this information. And it's also something which is useful for laboratory plasmas also. One other contributor for PlasmaPy, I think, was working on this in the context of a stellarator, which is a really windy fusion device, different than a tokamak. Hard to describe without a picture. All right. So let's create an ionization state object for helium-4. And in this case, we're saying it's exactly as above, 10% helium 0+, 70% helium 1+, 20% helium 2+. We're specifying the density of the element also. So this 10 to the 7 particles per cubic centimeter. So let's press Shift Enter. And then if we want to get the ionization state information back, we can do HE states underscore equals, ionization HE states dot ionic fractions. And then we can get this information back as a NumPy array. Here's a question from Will on Slack. Is ionization state a subclass of particle list? No, it is not. Though there's a lot of functionality in particle list that is used within ionization state. So that is a good question. All right. And the next thing is we can get the symbols also. So let's do HE states dot ionic symbols and Shift Enter. And we get HE4 0+, HE4 1+, and HE4 2+. So as expected. And because we provided the number density of helium, we can get back the number density of each ionic level. So HE states dot number underscore densities. Shift Enter, and we get, after it formats, 10 to the 12 per cubic meter, 7 times 10 to the 12, and 2 times 10 to the 12. We can also get the electron density under the assumption of quasi-neutrality, and that the entire plasma is described by this. So it's not missing any elements. So if we do HE states dot n underscore e, we can get that the number density of associated with the missing electrons is 1.1 times 10 to the 13 per cubic meter. We can also provide an ionization state with a charge number as an index. So let's do that. HE underscore states of, let's say, 1. And then we can get another object, which is an ionic level object, which corresponds to that particular level. So it was 1 here, and that's the index. So it corresponds to helium-4, 1+. And it will give you the ionization fraction also. And this is useful if you want to iterate over ionization states. The next thing that we can do is get information about the average charge state. And since average can mean a couple of different things, we have a few different possibilities. So we do HE underscore states dot Z underscore mean to get the mean charge number. We can get HE states dot Z most abundant and get a list containing the most common charge numbers. It's a list because there can be more than one charge number at the same, with the same abundance. And then finally, we can do HE states dot Z RMS for the root mean square, and it'll calculate that for us too. And so this ends up being pretty useful because there are times where you need the mean charge number. There are times when you need the root mean square charge number. And then it's also helpful to know what the most abundant charge states are. We can also calculate the properties of the average ionic level. So let's do that. HE underscore states dot average ion, and we call that. Shift enter, and it gives us a custom particle. And it did the calculation for how many electrons got removed from the mass, and then what the average charge number or charge is. And if I remember correctly, it corresponds to Z mean. We can also use the summarize method to print out a nice summary of the charge states. So we do HE states dot summarize and then call it with parentheses. And we have a nice printout where it says ionization state instance for helium-4 with the value of Z mean. It gives the ionic fractions. It gives the ion densities, gives the density of the element as a whole, so the sum of this column, and then the electron density. So it's a nice quick way of seeing what's in it. So the next thing that I want to do is to look at some actual average ionization state data. And this is for a particular interplanetary coronal mass ejection observed by ACE at about 1 AU. And this particular ICME included a lot of cool plasma. What is neat about the Gilbert et al. Paper is that usually there are limitations on what charge states can be observed or inferred from ACE observations. But with their special processing, they were able to get to pretty low charge states. So carbon 1+, oxygen 1+, and then for iron, down to like iron 2+, and up to iron 20+. So there's a really broad range of charge states. And so let's press enter. So in this case, we created a dictionary with the atomic symbol as the key, and then the the number densities as the value. So a quantity with the number densities in units of per cubic centimeter. So the next thing we can do is use this information as an input for another object, ionization state collection. So let's do that. Say states equals, whoops. States equals ionization state collection, and then in parentheses, number densities. And then shift enter. And so this created states, which is an ionization state collection object. The difference between ionization state and ionization state collection is that ionization state is for a single element or isotope, and ionization state collection is for multiple elements or isotopes. And a lot of their functionality is pretty similar. If we take, if we do states and then provide it with an index of, or key of C for carbon, then we end up getting an ionization state instance back. So you can iterate over the ionization state objects that are within ionization state collection. We can also get the relative abundances of each of the elements. And that is with states.number densities, which will give us another dictionary with the object. Oh, sorry, I'm getting things out of order. Wait, let's try this again. States.abundances, which will say that in this case that 0.18 carbon atoms, 0.81 oxygen atoms, 0.006 iron atoms correspond to average. So this is like the fraction of the element over all of the atoms among all three elements. And in this case, it was calculated automatically, but you can put in arbitrary numbers here so they don't have to be normalized or add up to 1. Often it's a bit tricky to look at the absolute abundances. So let's look at states.log abundances. And this will give the same information, but in log base 10 space. And if you're looking at hydrogen as well as a lot of the other elements, carbon, oxygen, iron, silicon, nitrogen, etc., then this ends up being pretty handy. And often the abundances are provided in this form to begin with. Okay, now we can get back to where I started to type before. We can also get back the number densities. So states.number densities, and we get the same inputs, except in SI units. And then again, we can calculate the electron density with the n_e attribute. And so this electron density corresponds to all three of these elements for all of the ions, and it assumes quasi-neutrality. All right. And the next thing that we can do is, again, print out a summary of the information. So we can do states.summarize, and then specify minimum ionic fraction equals 0.1 in parentheses. And shift enter. And with this command, we end up getting, again, a nice summary that is similar to the one for a single ionization state, but it includes the ones for or information for carbon, oxygen, and iron. And it only includes ions with an ionic fraction of greater than 10% for that particular element. And this distribution is a little weird because iron 4+ and 5+ are above 10%. And then iron 6+ and 7+ aren't. And then iron 8+ and 9+ are again. And then we can make some plots. And I didn't feel like typing all that out, so I included it there. And we can see that in this log scale, that carbon 2+ is most abundant. Oxygen 2+ also is most abundant. And then there are a lot of carbon atoms that are at fairly high charge states, and for oxygen also. There's some between oxygen 1+ and 8+. And for iron, it goes from 2+ to 21+. So it's a pretty broad distribution. And I want to ask the question, does this plasma look like it all came from the same temperature? So feel free to respond in the chat. What do you think about this? And feel free to use emojis also. The head blown emoji does describe it accurately. No, it doesn't. Sweat smile emoji. Nope. Right. Yeah. Someone pointed out in the Twin Peaks and Oxygen, or in the Zoom chat, that there are peaks and multiple peaks for oxygen. There are multiple peaks for iron, and then a little bit for carbon also. So this is a pretty weird ionization state. And one thing which I probably forgot to mention is that this is an hourly average, because my understanding is that they needed additional signal to noise for the low charge states. And so in this hour, when observing this ICME, there was filament material, cool plasma, at the same time as hot plasma. And this means that, or one thing that we could quite probably take away from this is that the heating of this plasma and the initial temperatures also are patchy. Like the heating is different plasma ended up getting heated or started out at different temperatures, which is not surprising because the corona has a bunch of multi-thermal plasma. So this was a fun paper to look at. I was looking through the literature for some good examples, and this was the most interesting one that I could find. I do want to mention that if you really, really like these plots, one contribution would be to add methods to ionization state and ionization collection in order to make these plots. That's something which has been on our to-do list since probably about 2018. But yeah, that would be a really helpful thing to add. One other aspect which I wanted to mention is that in the future, we want to improve the compatibility, interoperability of ionization state and ionization state collection with actual observational data. So to be able to take composition measurements of the solar wind taken by ACE or solar orbiter, and then put them into these data structures and be able to plot them and do science with them, and also do non-equilibrium ionization modeling. Apologies if you can hear the alarm. There's a fire station down the hill. All right. So yeah, this was this was neat. It was fun to plot this and look it up or try to understand it. And the paper was, again, somewhere. Gilbert et al. 2012. And a link to it is in the notebook. Okay, so the next thing that I wanted to cover is PlasmaPy.formulary. And I think about 45 minutes left or so. So we already imported it above, but we can import it again. What PlasmaPy.formulary contains is a broad variety of the formulas needed by plasma scientists across different disciplines. And if I have it handy, nope, I don't. Oh, I do. There is the NRL Plasma Formulary, which you can order free online. And that contains a whole bunch of different formulas and useful stuff needed by plasma physicists across disciplines. It's pretty useful to get. Yes, and it's worth all those heart and thumbs up emojis also. So we've implemented a lot of those. It turns out that it only took us about a year to come up with the name of formulary, despite how familiar we are with the plasma formulary. Names are important. So the first one is going to be plasma beta in the solar atmosphere. And if you're not familiar with it, beta is the ratio of the plasma pressure or gas pressure to the magnetic pressure. And I had to read that because I tend to forget when I'm talking what it is. What this means is that when beta is much greater than 1, then the magnetic field doesn't have, it's not strong enough to be able to exert that much of a force on the plasma. And so the motions tend to behave more like a gas. And when beta is much less than 1, then the magnetic field is pretty strong, and magnetic tension and pressure end up being the dominant macroscopic forces. So we can use PlasmaPy.formulary to calculate plasma beta in different parts of the solar atmosphere. If I can find it. Okay. And let's define some plasma parameters. So let's say B corona equals 50 times 50 Gauss. And then N corona equals 1E9 per cubic centimeter. Oops. And T corona equals 1 megakelvin. So these are characteristic plasma parameters for the corona. Right. And then we can use beta. So beta, and call that of T corona, N corona, and B corona. And we get that T corona is not defined. And this error usually means that I did not press Shift Enter to execute the notebook. Let's see. And there's a question in the chat. Is beta the parameter used to indicate the stability of a star? No, it's a fundamental plasma parameter. So it's something that gets used for laboratory experiments, stellar atmospheres, plasma in the ISM, and so on. But in terms of fusion devices, usually the beta value can only get up to like 0.3 or so, and then you start to have a whole bunch of instabilities. So it does end up being pretty relevant to stability. All right, there's this, And yes, we get the value that was posted in the chat in Slack also, of that beta for the solar corona is about 0.1%. So the solar corona, as we know, is magnetically dominated. And then we can do this for our favorite layer of the solar atmosphere, for some definition of favorite, the chromosphere, and do B chromosphere equals, and the chromosphere is kind of a mess. So we can put in a range of magnetic field strengths. So between 40 and 200 Gauss. And then let's say the temperature of the chromosphere is about 6225 Kelvin. And then N of chromosphere equals 2.711 E13 per cubic centimeter. And then I'll remember to press Shift Enter this time. And there's a question in the chat. Will a beta calculation work if you put it in different units like nanotesla? Yes, it will. As long as the same physical type is, as long as the quantity has the same physical type, then it will work. Along those lines, it's also possible to put in temperatures in terms of electron volts as well as Kelvin. So we can maybe do one example of this, 6.225 kilokelvin, which is not a unit that I hear very often. And then we can do beta of T chromosphere, N chromosphere, and B chromosphere. And then Shift Enter again, and we get a range. So beta for this part of the chromosphere for this range of magnetic fields could be as low as about 0.36, or sorry, as high as about 0.36, or as low as about maybe a little over 1%. So there are times where the chromosphere is magnetically dominated and times where its magnetic forces are more important, but you can't ignore the pressure gradient force. All right, and then for the quiet sun photosphere, we can do this again. Oh, so B is the magnetic field, and we got this, or I got this from an observational paper that did some estimates, because it's pretty hard to find what the magnetic field is for the chromosphere. All right. And so we can define temperature of the photosphere as 5800 times U dot K. B photosphere equals maybe a bit higher. So let's say 400 Gauss is the magnetic field. And then the number density of the chromosphere, or the photosphere, might be about 1E17 per cubic centimeter. All right, and so these are characteristic values of the somewhere a typical region of the photosphere. And we can calculate beta again. So beta of T photosphere, N photosphere, and B photosphere. And that will give about 12.5. So the quiet solar photosphere is pressure dominated. So the magnetic field plays some role, but it's not the most important. We can also look at a sunspot. So say the temperature of a sunspot, it's going to be a bit cooler, so about 4,500 Kelvin. And then B of a sunspot equals 2 times U dot kilogauss. So pretty strong magnetic fields. And then we can do that. And then we can calculate beta again, which is beta of T sunspot N photosphere, since that is going to be about the same, and then B sunspot. And we get that beta is a bit less than 1, about 0.4. So in sunspots, the magnetic field is more important than the pressure gradient force. So there's another question about, for the beta, could we add different temperatures for electrons, protons, and other ions? At present, no. We're not able to do that. But let's see, if I remember the math right, you could calculate beta for each species and then add the 3 of them together. I think it's additive like that. All right. So yeah, that is using beta to calculate beta. One of our goals with PlasmaPy is to have our notebooks be educational also. So we made sure to have opportunities. So if you end up having to teach a plasma physics course, might be able to use some of these notebooks as well. All right, the next thing is to calculate some plasma parameters in Earth's magnetosphere. And for this, let's look in the context of the magnetospheric multi-scale mission. What MMS is a constellation of 4 spacecraft that take measurements of density, magnetic field strength, and so on in Earth's magnetosphere. And they're studying the physical process of magnetic reconnection. And I don't want to go too much into detail about this, but reconnection is a fundamental plasma process that converts stored magnetic energy into thermal energy, kinetic energy, and particle acceleration. And it's a process that powers solar flares and is a driver of geomagnetic storms in our magnetosphere, and happens when the D side of the magnetosphere interacts with the solar wind. It's important in most magnetized plasmas because, for example, in magnetic confinement fusion devices such as tokamaks, reconnection can make it harder to confine the plasma. So it's an important physical process that happens in the heliosphere, and it can be studied in the lab. And the general setup is that you have 2 magnetic field configurations that are pushed towards each other. And then there's some resistive diffusion. The magnetic field ends up slipping and canceling out. And then as stuff goes in, there is an outflow that is happening at about the alphane speed. All right. And so this is the classical picture of it. And there's a length of the current sheet and a particular thickness. That model is the classical model. And if we think about a situation where reconnection is happening on really small length scales, it ends up being the case that the electrons and the ions move at different velocities. The electrons have not much mass, and they can go in and go at like really tight angles. But ions are pretty bulky, and they kind of need to get accelerated pretty slowly. And these two length scales are known as inertial lengths. And the inertial length is a pretty important plasma parameter, especially in the context of MMS. So an inertial length is the characteristic length scale for a particle to get accelerated by electromagnetic forces in a plasma. So if you want to accelerate a plasma or accelerate an ion or an electron or decelerate it, if you want to change its trajectory, this is going to be the characteristic length scale for it. And the reason why this is important for MMS is that there is an inner electron diffusion layer that's the size of the electron inertial length, and an outer diffusion layer, which is the scale of the ion inertial length. And when people were trying to design MMS, one of the things that they needed to do was to figure out how far these spacecraft need to be away from each other. And the answer is somewhere between about between the electron and ion inertial lengths. So let's do the calculation that they did when planning it and figure out how far the MMS spacecraft should be separated from each other. So our mission, we're going to calculate the ion and electron inertial lengths. Okay. Yeah, this is a really fun topic too. MMS is a really neat mission. You can get like really high resolution compared to what you can do in the laboratory. Like in the laboratory, it's really hard to measure things like electron distribution functions to get down to the inner scale of this. But in the magnetosphere, it's not easier, but it's more possible, I should say. So yeah, let's get some plasma parameters. So the number density N is equal to 1 per cubic centimeter. And then the magnetic field is maybe 5 nanotesla. And then the temperature is 10 to the, let's say, 4.5 Kelvin. So hard to do anti-logarithms in my head, about 30,000 Kelvin or something like that. If someone has NumPy open, you can do that calculation. Or actually I do, so I could have done that. Oh well, I'll leave it as a mystery. Okay, so we have that information. And now we have what we need to know to calculate the ion inertial length. So on scale shorter than di, shorter than the ion inertial length, the ions and electrons are going to decouple from each other. So they're going to be moving at different paths through the reconnection layer. Let's calculate inertial underscore length, and then the number density, and then let's do this for a proton, since that's the most common ion. And we get that it's this value. But it's hard to keep track of decimal places. So let's do 2 and then say km. So the inertial length is a few hundred kilometers in general. And so chances are we're going to want MMS to be separated by less than a few hundred kilometers, which if you're sending stuff in orbit, that's pretty difficult from what I gather. All right, so now we can calculate the electron inertial length. Do inertial length, then n for the number density, and then E minus. And then, so I don't forget this time, to Km. So we're using the same number density and only switching the protons to electrons and then converting to kilometers. And it's about 5 kilometers. So it's pretty short, especially compared to an Earth radius. Okay. And then while we're at it, we can calculate the gyroradia for different particles. So the radius at which a charged particle gyrates around the magnetic field, also known as the Larmor radius. One side comment is that we decided to use the term gyroradii because it is pretty intuitive, is a lot more intuitive than Larmor radius. And that physical intuition does help when reading code. So choosing variable names wisely is a very valuable skill. All right. This is where we need the magnetic field for. So calculate the gyro radius for 5 nanotesla, what we specified before, that magnetic field strength, for a proton, and for the temperature that we defined. And it'll be 2 kilometers again. And so the gyro radius of protons is going to be about 50 kilometers, at least away from the reconnection region. And then the gyro radius of an electron will be so use the same magnetic field, change it to an electron, and then we're getting the thermal velocity via the temperature. And so the gyro radius is just a kilometer or so of electrons. So the length scales that we have, yes, this is assuming thermal velocities, and it is the classical gyro radius. Responding to a question in the chat. As I comment, we're going to extend the gyro radius function to be relativistic, and hopefully that'll be done by the next release in a few weeks. Not for certain though. All right, so the characteristic length scales range from a kilometer to a few hundred kilometers. And it turns out that the MMS spacecraft are separated by, at minimum, about 10 kilometers, and at maximum, a few hundred kilometers. So they wisely chose the length scale for which to separate the 4 spacecraft. They're really getting a good view of the reconnection region, and they've discovered a lot of new ways that reconnection can occur. So if you have a chance and are interested in reconnection and like geomagnetic substorms, which is a really cool phrase, then I encourage you to check out the results from the magnetospheric multiscale mission. And then we can also calculate some of the frequencies. So let's first calculate the plasma frequency. And that's for, use the same number density. And let's do this for protons. And we get about 1300 radians per second. what the plasma frequency is if you have a plasma just hanging out, you have a bunch of positively charged particles and a bunch of negatively charged particles. And if you put a particle in it, it's going to oscillate at about the plasma frequency. So it's a pretty fundamental plasma frequency. And let's calculate the plasma frequency for electrons also. And it's a lot faster, which is not surprising. Electrons are tiny, and so they would probably oscillate a lot faster. And if I had finished this notebook in time, I would have put in a discussion about how the plasma frequency feeds back into MMS design decisions, so like the time resolution of the instruments, but I didn't get finished soon enough, so you'll have to check out PlasmaPy's documentation in probably a few weeks. So look forward to it in the future. All right. The next thing we can do is calculate not the gyro radius, but the gyro frequency. And for this, we only need the magnetic field. And we can do this for a proton. And we get that it's about half a radian per second. So it's fairly slow compared to the plasma frequency. And then the gyro frequency for the same magnetic field for an electron. And this is going to be a lot faster. And then PlasmaPy also has some frequencies that we don't use very commonly in heliophysics, but we use sometimes. And one of them is the lower hybrid frequency. And that requires, we need to know the magnetic field, the number density, and which ion. And that gives you about 20 radians per second. And if you want to learn more about the lower hybrid frequency, the doc string for it contains some more information about it. And I think at least for, I think the most recent one is in, it got updated kind of recently, but I think it was in the 0.7 release, so it should be there. All right. So we have about, I think, 20 minutes left. And let's start working on distribution functions. And then after that, we'll have Coulomb logarithms. Those are fun. All right, so, let's see. If the question or comment in the chat is, I'm curious if this function works with input parameters given as an array or a list. And so right now, we don't have the capability to put a particle list for the ion, though one of my hopes for PlasmaPy later this year is to enable that functionality. But we can do this for, let's say, 1 and 5 and 10 nanotesla u.nt instead, and we can get the array out. So we can do this for quantities, and we should be able to do this for all formulary functions. So if you happen to notice one where it doesn't work, then please let us know and we'll get that fixed ASAP. And then, yeah, later on, we hope to make this possible so that you can do something like electron, proton, and alpha, or something like that. but that doesn't work yet. Okay, so, okay. All right, I'll pause a moment in case there are any other questions from in person or the chat. And so I don't like lose my voice. This is a lot more talking than I usually do. Okay, the question is, why is the lower hybrid frequency the same as the gyro frequency in the case of electrons? I don't actually know. Let's see. I might save that or respond to that later. So I will say, remind me about this in 20 minutes. And so I'll try to respond to that question during the lunch break. Hopefully I can. I tend to prefer not to think about plasma waves, so I might need to ask someone else. All right. And so the next thing is distribution functions. So in PlasmaPy, we have a few distribution functions for Maxwellian 1D, 2D, and 3D. For the moment, let's look at the 1D case. And so let's define the probability density as Maxwellian underscore 1D. Oops, caps lock on. D is a hard letter to spell. Okay. And so Maxwellian 1D, and let's say the velocity is 500 kilometers per second. And then T equals 30,000 Kelvin. And let's do this for a particle being an electron. And then let's calculate that, and then let's print it also. All right, so with that command, we're getting the probability density for 500 kilometers per second for a 30 kilokelvin plasma for an electron. And it ends up being about 4.5 times 10 to the minus 7 seconds per meter. And this means that if we integrate this over speed, we'll end up getting a velocity. And so let's do that. Let's say T equals 3.4 so 30,000 Kelvin. And then let's do a velocity resolution of 1 meter per second. And then do V as numpy dot a range of minus 5e4 to 5e4. 4, and then have a step of 1, and have to be times meters per second. All right. And so we can do this. And then I didn't feel like typing this out, so we can do that again. And if we do the integral, we get that it's about 1, and we can do that for particles also. Let's see. All right, and that is handy. So we have that distribution function. Okay, and then we can also take the standard deviation of this distribution function and get back our temperature. And if we do that calculation using physics equations that I can't quite remember what they're called, ideal gas law maybe, and then we get back 34,000. Oh wait, hold on. I think there's an issue there. Ah, here's where it is. I had the wrong units. So it was working right. And now that plot looks better. And then if we do this again, we get, oh, what happened? Yeah, this should be showing up different, but it's, oh, sorry. No, it's right. Okay. We have it converted to kilokelvin, so we have the right units. Yes. Okay. I got confused about that. So thank you for your patience. And let's see. So there is a question, can we convert plasma frequency to hertz? And yes, there is a 2HZ keyword, and that will give you, oh, wait, hold on. Might be this. Yes, okay. There's a 2HZ keyword where it'll convert it to hertz. So it will do the 2 pi difference with angular frequency. And the documentation should say more about this. And another question is it possible to calculate kappa distributions? And yes, it is. There are, I believe, kappa 1D, kappa 2D, and kappa 3D functions in there, if I remember correctly. But yeah, that is an important capability. All right. Since we're getting short on time, I'll go over this fairly quickly. For the thermal speed, there are 3 different speeds that we can, or 3 different ways to calculate it. And it's actually kind of confusing and annoying that there are these 3 different ways, and sometimes papers will not specify which method that they're using. So there's the most probable thermal velocity, there's the root mean square thermal velocity, and then there's a mean magnitude thermal velocity. And there is a, if we specify a temperature, so 100,000 Kelvin, oops, and then speeds equals np.ln space, so an equally spaced array between 0 and 8e6. Let's do 600 points times u dot m u dot s. And then we can get a probability distribution function for 3D, which is Maxwellian speed 3D. And then have to be speeds t equals t and particle equals e minus. So we have that. And then we can do the most probable is equal to thermal speed, t equals t, particle equals e minus, and then method equals most probable. And then we have to specify the dimensions. So we say ndim equals 3. And I will copy and paste this as a shortcut. So we're short on time. And then v root mean square method equals RMS. And then the mean magnitude. And then we change this also to mean magnitude. So now that that's defined, we can do a pretty plot and see for a 3D Maxwellian distribution function, we have the probability density, and then we can get the most probable, the mean magnitude, and the RMS thermal velocities. And they're close, but they're a little different. So it is something that you do have to take care of or to think about. All right, and then keep scrolling down. So Coulomb collisions are collisions in plasmas where you have two charged particles and they end up interacting with each other due to their electric fields. So you could have two protons that go towards each other and they get deflected slightly, as one example of that. And they occur at a range of impact parameters. So you could have them going at maybe this distance for a short impact parameter, or distance for a longer impact parameter as their initial trajectories. And in a plasma, there's going to be a range of impact parameters, and you have to decide what to choose for the inner length scale and for the outer length scale. And instead of getting into that, I'll mention that PlasmaPy has a way to does the choice of figures out what the inner impact parameter and outer impact parameter should be to calculate the Coulomb logarithm. So I will do one quick example and then open it up for questions because I'm short on time. So say for a 1 megakelvin plasma with an electron density of 1e15 per cubic meter, and then species equals E minus and P plus. So these are the two particles that are colliding, or the two particle populations. And first we can get the impact parameter for this, T n sub E and species. And it says the range is between really short, 10 to the minus 11 meters to about 2 millimeters. And we can calculate the Coulomb logarithm and get T n underscore E and species again, and get that it's about 19. And the reason why I like this functionality is that it's pretty common for, if we wanted to create a function for Coulomb logarithm for like astronomy, pretty much the value would be return 15 and not really do the actual calculation. So this gives you a bit more accuracy with not much additional effort. All right. And the last thing, we have functionality for calculating thermal Bremsstrahlung, free radiation. calculating those horrible Bergrinsky transport coefficients like resistivity and viscosity and thermal conductivity. We have some functionality for calculating magnetostatic fields. And we have some functionality for calculating dispersion relationships, which I'm just executing all of. And I'll get there eventually. And so in this last plot, we can get for a two fluid plasma, the fast wave as a function of angle, the alphane wave, shear alphane wave, and the acoustic wave.
Hey, Nick, can you slow down just a little bit?
Yeah, I was just about to finish up. So just wanted to mention that we do have that functionality for dispersion relationships. All right, and I guess I can slow down a lot because I'm done. And so, oh wait, is it done? Oh, do I have another 15 minutes, Julie?
No. You have 2.
Okay, cool. So I'll open it up for questions. And awkward silence. So the question is, what is the difference between alphane and acoustic waves? So alphane waves, the restoring force is magnetic tension, and the alphane waves propagate along the magnetic field at the alphane velocity. Acoustic waves have both plasma pressure and magnetic tension, or I think it's have both plasma pressure and I think it's also magnetic pressure as the restoring force. So for the slow and fast magnetoacoustic waves. So there are a bunch of different waves that show up in a plasma. Let's see, so for next question is about ion neutral magnetoacoustic waves. Let's see. I think what I'll do is post a response to that later in the chat. I can show, I have some slides from 6 years ago that can get into that. Let's see, is there any functionality to get energy spectra? Let's see. Not that I can recall at the moment, though. There might be something in there. Our wave functionality is still pretty new, so we have a lot more to add. And we also want to be able to calculate this sort of thing for plasma instabilities also. All right. Do you plan to add emission distributions? Do you mean like differential emission measures, or?
We'll leave that question to be asked.
Okay. All right.
Awesome. Thanks, Nick. That was awesome.
Sure. And in the PlasmaPy channel, near the top of it, one of the pinned posts is a bunch of links, and at the bottom of it is a way to set up a meeting with me, so a scheduling link. So please feel free to set up a time to talk to me. And also I'll try to respond to questions in the chat for this afternoon or evening there. But otherwise, apart from that, thank you so much.
Thanks, Nick. All right, it's time for the coffee break, everyone. Back at 6:15 p.m.
All right, can folks at ESAC hear me?
Yep, we can hear you.
Awesome. I was afraid I was going to have to do like a raise your right hand if you can hear me and your left hand if you can't hear me.
Not that you can really, I guess you can see us. There you go.
I can see the back of your heads, which is a very interesting experience. So we're about to try another adventure here, which is now can you actually see my screen?
Yep.
Fantastic. All right. Just let me know when you're ready for me to roar.
I think we're all here, so go ahead.
All righty. Well, thanks, folks. Wanted to introduce you to SpacePy as one of our PyHC packages. And I am not doing like Nick and trying to do this tour de force of an awesome one-man show. I'll have Steve Morley and Dan Welling supporting me. Wanted to give you a very quick overview of the package first, and then we'll dive into, we've got 4 examples for you because that's really the best way to show what's going on. So SpacePy, really think of as just one tool in the box, part of the bigger ecosystem, where obviously, as we all know, NumPy is really our nice array library. SciPy gives a lot of stuff that's somewhat domain specific. Matplotlib gives the plotting. And then SpacePy sort of interacts with all of those and complements them. And of course, now with our broader ecosystem, making connections out to other packages as well. So I think I'll skip this because this is way out of date. But really, again, we're part of a bigger ecosystem. We have a pretty wide range of intended audiences that sort of complement what these other packages do. So what's our scope? We're, of course, open source. Being a PyHC package, we made the, in retrospect, probably poor choice to use the Python Software Foundation license. And our first public release was actually 11 years ago. So we've been at this for a bit. We're primarily intended to be a toolkit or a library, not necessarily an application. If we can do something that supports something soup to nuts, that's great. But the main thing is making sure that all of those building blocks are in place. And our main interest is really from the heliosphere to the magnetosphere and down kind of to MI coupling, which basically matches our main research interests. And in general, we try to have our development be driven by need. So that's science studies, that's data set production for missions. And that's not just the needs of us, that's the needs of any of the users, but still being driven towards something specific. We have a data model that's very lightweight. It's similar to HDF5. And the goal here really is just having a simple container that can carry along some attributes to describe features of the data. And that supports actually quite a few different metadata standards. And that's kind of the center of how we move things around between various file formats. And you'll see a couple of different instances of that this evening as we go through our examples. One of the things that's coming up that's pretty exciting is something that John Vandergriff is the PI for, and Sandy is doing a lot of the lifting, where we're really working on being able to move between a wide range of different data objects, different file formats. Our first sprint on this is going to be actually in July, if I'm recalling correctly, or maybe it's late June, but it's coming up soon. And this will let us do a lot of moving around between NDCube, SpacePy, and Happy. All right. Obviously, we've got a lot of documentation. We try to break this out into both a quick start and a class reference. Pretty wide range of models in here. Some of this is done internally. So we have, for instance, the A9, AP9 empirical radiation belt model, some empirical PlasmaPy models. We also do incorporate the URBM library that then supports an awful lot of magnetic field models and tracing through there. Whole bunch of tools. As I mentioned, we have some tracing of field lines and drift cells, some superposed epoch analysis and association analysis that we will actually show you later on, interface to the NASA CDF library, some nifty little tools for plotting. So it's just kind of a grab bag of things that we've found useful in getting both our science done and our mission support done. Just to show a couple of things have changed lately. We've gone and overhauled our time system so that there's fewer surprises hiding in there. That includes handling the rubber second era, which if you don't know about it, you don't want to. Let me just say fractional negative leap seconds and leave it at that. But more fun is we now have support to and from the AstroPy time. So if for some reason you have something coming in from AstroPy and want to use it in the SpacePy time system, that works, and vice versa. Our urban handling we've updated again to be handle least surprise. So if you throw in a coordinate that a routine doesn't support, it'll go and convert the system for you. Steve has been doing a big update to coordinates. This just came out. So we've been using URBM as our backend. There is now a pure Python backend available that's actually a higher precision and manages to keep the speed up there. This is not completely replacing URBM. The mapping is still based on URBM, but the coordinate conversions now will actually use either. And that also, unrelated, but same time change, is that we now, as with time, go to and from AstroPy coordinates. So this helps us play with the AstroPy system. Also, we expect to go and extend things into having more coordinate system support going forward. A couple of little things in the CDF support. We got do sparse records. We have UTF-8 support now since NASA just added that. So you too can put smileys into your attributes. And then we've just done some background updates, some installation stuff, some pathing of libraries on Windows, some handling of the .SpacePy directory. So I apologize. I've got like 3 monitors, and that's still not enough windows. So I'm just going to do a quick check if people have questions in the Slack. Cool. The Slack is frozen for me. So I'm going to blow through this quick, and then I'll double back at the end. So just want to show a couple of the cool things that have been enabled by the work here. So Steve Morley did this. This is using the GPS particle data to analyze dropouts using the superposed epoch analysis, both in 1D and 2D form. And so we're also getting a lot of other information from the SpacePy routines using the Shua model for the magnetopause standoff, L-star calculations through URBM, and the confidence intervals on here are bootstrapped, which we'll talk a little bit about the bootstrapping. Here's some space weather modeling framework output. Dan does a lot of work with this. We'll show you a couple more. This tutorial will go through in detail the point processes module and how you can look at associations between different events. Again, in this tutorial, we'll talk about the transforms and the coordinate rotations using MMS as an example. There's some spectrogram binning stuff in there. So if you have time series of data, it will bin it out to more regular grid. Less colorful, but this is also the baseline of our public release data for Parker Solar Probe. Sorry, was there a question? All right. So a couple more interesting things. There's a fairly recent paper on storm predictions using statistically, and just some simple stuff like just doing L mapping so that you can, this is with a CubeSat, so getting the L mapping out from that. Recent space weather paper on modeling the response to sort of an ideal coronal mass ejection, which again, Dan will take you through later. And some stuff that's coming down the pipe shortly. More space weather modeling framework support, in particular supporting the 3D output directly, doing slices. We have a neural network-based L-star calculation that is being updated to NumPy-based backend, so that's removing the requirement for Fortran for that application. And as a plus side, it's also faster. As I mentioned, we've made some improvements to coordinates, going to be defaulting to that Python backend and support more coordinate systems. And just in general, we're in the process of killing off the old, so we're going to actually chainsaw out the Python 2 support and distutils and make pip the primary, not just an additional support. Part of that is also going to be, as folks are moving towards binary installers more commonly, we'll be increasing that and probably pre-packaging more stuff with the binaries. Really, installer is always something we're working on. And do some overhaul of our documentation. We've been updating the documentation regularly, but sort of the structure is actually original. So that'll be reworked based on experience with a different project. All of this gets coordinated through GitHub. So really our best way of interacting with you, if you've got a question about something, is the discussions in GitHub. If you want to see kind of what we prioritize next, we set up each release with a project in GitHub. So that is really the key way we interact with people. And I just want to make one more note here. When we start opening up our notebooks going into these examples, we've delivered those notebooks as Markdown. They're plain text. And you just need to know that in the HelioCloud environment, in order to open them up in Notebook, you need to right-click on the name of the file, do Open with a Notebook. And what the difference here is these are basically text documents that then act completely as notebooks, so that you can look at them as plain text, or they can be live like the other IPython notebooks. So I'm going to stop my share, and I'm going to see if there is a chance I can get Slack to actually load and see if there are questions in there. Cool, my Slack has actually completely died. Alrighty, so Steve is going to go and do the first example looking at the MMS ephemeris, and I think some of the magnetic field data. So go ahead, Steve.
Right, so hopefully everybody can hear me, and I'm also not having technical issues. How does the screen look? Can someone give me the world's biggest thumbs up so I can see it? I'm just going to assume that my eyes aren't working. Okay, so as John mentioned, we have all of our notebooks as Markdown, and so this uses the Jupyter text. Yes.
Just real quick, can you zoom in a little bit? It's a bit small for us.
Oh,
that went worse. Okay, that's better. Thank you.
That's better?
Yeah, that's
okay.
Great.
Yeah, so the notebooks are all delivered as Markdown, and this is using the Jupyter text extension to Jupyter. If you're using Jupyter locally, just double clicking this will open it as a notebook. If you do that here, well, it gives you Markdown. And the good thing about this is that it makes version control a lot easier to read. If you make a small change in this, it's not going to be updating a whole bunch of XML and possibly any binary outputs you have from your cells, like if you have plots or things. It'll always save a clean notebook for you. So here, like John said, open with notebook. Let's just get rid of that launcher. So does this help? There we go. Okay, so, and I'm in totally the wrong one. So let me just open the one that I'm supposed to be talking about right now. Okay, so this is an introduction to just using, to working with some data and largely looking at the coordinate transforms. We're using NASA's magnetospheric multiscale mission as an example. So one of the instruments for that mission is the MEC mission, and that is the MEC instrument. And that's magnetic ephemeris and coordinates. It's not an instrument that's on the satellite. It's a supporting team that provides data for position and attitude, as well as some derived quantities. And so I'm going to kind of work with that data product as sort of a walkthrough of some of our coordinate capabilities. And so I'm not sticking strictly to the SpacePy ecosystem. I'm trying to work with, in a way that you might work, just so you get an idea of how you might use this. There are some notes here about data files. If you honestly, if you see anything that says version 1 from MEC, from the MMS mission, just ignore it. There was a different quaternion definition that was used at the start. Okay, so setup. John mentioned leap seconds. That's something that can be handled in a range of different ways. Either you can assume that you're always online and just grab that information. I believe that's how AstroPy does it. We bundle stuff with SpacePy, but then also have an update routine in Toolbox, which will update all of the various ancillary data products that we need. So this data is usually maintained on a per user basis, and obviously on a shared environment like this Helio cloud, that gets a little trickier, making sure that everybody has everything up to date, blah, blah, blah. So we have set up a shared directory that has the normal SpacePy configuration and all of the managed data. It also has the data for the tutorial.
Hey,
so
Steve, quick one
yes.
more time. Can you zoom in one more?
One more.
Cool
is,
things. Yeah, that's good.
Let me see if I can move this. Oh, no, that's as small as I go. Okay. Right. So, yeah. So the so what we're going to do to start with is basically just, I've set this up so that all of these notebooks, because they're on our GitHub in the examples repository, if you're at PyHC, congratulations, welcome, you're right here. If you're watching this on YouTube in 3 years' time, great. Set this is PyHC to false. Everybody else right now, leave it to true, because this is the PyHC summer school. So, so all this is doing here is basically saying for the summer school, let's point it to where the tutorial data and everything else that SpacePy needs is. If you're not on Helio Cloud, that's just going to work out of the box. And so we're going to be running through a few things. I'm going to be using coordinates data model, toolbox, and plot from SpacePy. You'll notice also URL lib request. There's just an example of how to grab some data, which there are a number of different ways of doing it. If you're kind of old school, maybe you'll want to go pull something from a website. We've already done that for you. This data is now in the shared directory. So one thing that I do like to do if I'm kind of doing little scripts to work through things, so I like to make sure that I'm not repeatedly loading things or repeatedly downloading files. And so I just, like to write in little checks for, do I have this file already? So, it's a handy little scripting tool. So just check that the files are present, and if not, download them. Everything should be right here on the Helio Cloud server. Okay, so if those files aren't present, it will use URL lib from the Python standard library to go pull those data files down. And of course, you can script this. It's very easy to go grab lots of data as long as you know where it is. If you have to work a little harder, there are things like happy. And then here, this data is in NASA CDF format. DM is the SpacePy data model module. And we have a bunch of these different from routines. So there's from CDF, from HDF5, from netCDF4, read JSON headed ASCII. And so these all read into the same common form, which is essentially a dictionary that has attributes to contain metadata. and then a bunch of modified NumPy arrays that also carry metadata with them. And those can also be nested. They're not in CDF, but they can be in HDF5. So I'll just load that, and SpacePy's CDF support actually comes from the PyCDF module, which is a lot more flexible. These are convenience routines that basically suck everything in, and they do a read all at once. I will come back to that. So, let's just see what that did. I'm a big fan of inspecting everything I've just done to make sure I didn't do something stupid. It happens more often than you think. We have on this data model object, which is a space data, we call it, this has a tree method. If you're using just a regular dictionary or something else that's dictionary-like, it won't have that method, but you can use dictree from SpacePy's toolbox. It does the same thing. So there's a few things we can do. We can set verbose to true so that we can see a lot of, so that we can see what each variable is. And so in here we can see, this is just modeled off tree from Linux. And so you have like, some metadata here, the 3-vector representation, which is 3 elements, the epoch, which is 2880. There's also, as it says here, we can set the attributes keyword. So let's just do that. And you can see now all of the attributes have this little colon on the front, and this goes on forever. So let me just get rid of that and rerun the cell. Makes it a little easier to scroll past. So this follows the mission standard naming convention, satellite, instrument, product. And we'll come back to the ones that we're using of these. The MMS data itself is not the important part. These are just dictionaries. So you access everything in there in the same way that you would with a dictionary. And then all of the metadata is stored in this .attrs. Okay, so that's what that looks like. I don't like things that spill over multiple lines like this. So, let's just iterate over that and print it a little more pretty, okay? And so then this is using the NASA's ISTP metadata standard. We do also have a module specifically to help with working with ISTP metadata. So what we're going to be using out of here to start with is we're going to be using quaternions, and quaternions are it's a 4-element rotational construct. So they have their own whole system of mathematics, and they're used largely instead of rotation matrices. They're lighter weight, and they have a few other benefits. So I'm just going to use these to do some transformations of the MMS satellite positions from one coordinate system to another. And these values aren't calculated with quaternions, and they're not calculated with SpacePy. So this is a kind of an independent test. They're calculated with this Lanol Geomag package. We do implement a similar approach. There is one difference here, which, as you'll see, doesn't really impact the results. So we'll start with the position in GSE, that is geocentric solar ecliptic coordinates. And we're going to use our quaternions to rotate this. You may have quaternions for other missions, you may not. So the way that this is all given is we have in the data file ECI2 some target system. And that's basically, the quaternion you would use to rotate from an Earth-centered equatorial inertial coordinate system. So what we need to do is we need to go from GSE to GSM. So we get our ECI to GSE quaternion. We take the conjugate, which gives us GSE to ECI. And then we multiply that by the ECI to GSM. And we have to do that in reverse order. Okay. So we use in SpacePy coordinates. We have some quaternion math for this. And that gets us our GSE to GSM quaternion, which will rotate our vectors by. So there's some stuff here. I'm going to move through this relatively quickly because, you know, you'll probably don't care too much about quaternions. You may, like, if they do come up, this is how you can use them. GSE and GSM share the x-axis, so we should be able to verify. And this notebook is basically all trust but verify. It's really it's a test suite for users. So if we just change the print precision so that we don't spill things all over our screen, and then just print out, you know, the rotations of vectors in, and I'm setting here as my input vectors just a unit vector in X and a unit vector in Z. And you can print these out here and see that, well, we have one, essentially zeros, and then here we have a 0 and 2 non-zero values. There's a couple of representations for quaternions because you have 3 vector parts and a scalar part, and the scalar part can be the first or last element. We support that. That's just a keyword argument. So what we can then do is just say, okay, look, you know, are these 10 to the minus 17s important? This is the sort of thing that maybe you would want to check at some point. NumPy does give you this information. If you're ever unsure, you can actually go check this. It will print it out quite nicely for you. It'll tell you, okay, for this data type, we're just using floats. This is defaulting to a float 64. And so we have our error sizes and our max and min that we can represent here. Okay, so where are we? So let's actually rotate those positions, okay? So we take the first 3 elements of the GSE position, and then we rotate this into GSM, which we're doing here with quaternion rotate vector. Okay, and so we're using the GSE to GSM quaternion and the MMS data. And so you can see everything just indexes as normal because it's just an array inside a dictionary. They're just modified slightly. So the first 3 GSE positions, we have X, Y, Z here in kilometers. And the first 3 GSM positions are given here. The conversion error from where we actually did that rotation, you can see here we're down around 10 to the minus 11. And that's a nanometer. Okay, so we're doing an independent reproduction of those conversions. So I think that's pretty useful. We can do that differently if we don't have quaternions, and you probably won't usually. Then we can do this. You know, there was a useful discussion yesterday actually about the coordinates in AstroPy. And I particularly enjoyed, there were questions about, can you do these transformations for other vectors? And we will get to that. Okay, so to do coordinate conversions, you also need to know what time you're doing them for, because the axes of different coordinate systems relative to each other are usually time dependent. So for this, we're going to use the new SpacePy backend. So this is in SpacePy coordinates. We have a default setting handler. We set the values. We tell it not to use OBM because that's currently the default. And then we set this tolerance here is essentially for caching. If you need to do something that's maybe going to be using very high precision, very finely spaced times, you want to set this to 0, turn the caching off. I think it defaults to something like 5 minutes. And so, if you are just converting between, say, non-rotating coordinate frames, you need, tens of meters of accuracy. You can set that to 5 or even 10 minutes and it's fine. It will speed things up immensely. So then what we do is we take the times here. And so these come out from the CDF in a date time format. And we throw these into TikTok, which is our time handling object. So then we make a coords. So we put in just our last 3 elements here. So I'm just, just makes it nice and short, inspectable. We want to do this in ECI. There are multiple different ECI systems. We're going to specify here, this is ECI at J2000. Okay. After that, we need to say whether it's Cartesian or spherical. We support both. And then we add the times to that object. And then the conversion to any other supported system is fairly simple. You just say what system you want it in and whether that's Cartesian or spherical. So if we take these, the position vectors from the file in geo, this is Cartesian geographic, they're here. You can see that they are identical if we use SpacePy's coordinate conversion instead of the supplied quaternions. I say identical. The conversion error here is actually about 100 millimeters. I'm not tremendously concerned with that right now, considering it's an independent transformation. So there are some handy little boxes here, which I would encourage you to get to in your own time. So there's some gotchas that are listed in here, some things that you might want to look at by, say, changing the back end. You could even move this over and do, see whether you can use AstroPy and SumPy or something else. Okay, so this is where I'm going to just say, okay, now we're going to rotate arbitrary vectors, and we're going to do this with our quaternions to start with. So we'll grab a data file. Again, this data is already on the server. And so we're grabbing the Fluxgate magnetometer survey data. And, we have the file already, so it's not going to download. And where I used SpacePy's data model for this convenient read earlier, this is a large file. What if we had, it's not that big, it's like 80 megabytes or something. But if we had a really big file, maybe we don't want to suck everything directly into memory. So we do have this more direct interface to the CDF library. So we import PyCDF. And then we have our constructor here, which is just CDF. If you give it just a file name, it will open that file. It will not read anything. It does a lazy load. It loads just what you want when you call it. Now, because I'm opening it like this, we need to close it later. The alternative is that we can open it using a context manager. And so that would be, with pycdf.cdf as some name, and then put that inside that context manager. That, of course, works in the usual way. So we've opened this file. There's not really anything in there. So in Toolbox, we have Toolbox is, John described SpacePy as a grab bag. I would say that Toolbox is very much a grab bag. SpacePy, at least, is growing to be consistent, coherent. But we have tools in there which include handling times. For example, do you have times for series 1, series 2, and you say, okay, which ones of these are in an overlapping time range, or which ones are identical from each? The kind of thing that you might want to do. So here we're using T-overlap. There's 2 versions. There's T-overlap and T-overlap half. T-overlap half basically only does a comparison in one direction and therefore is faster. So what this is doing is it's finding all of the times in this this time variable that overlap with the times in the fields file. Okay. And because this is NASA CDF, we know that those times are stored using the same representation. So, as I said before, we can use this dict tree to see what's in this data file. Again, this is doing a lazy load, so it's not reading in all of the data. And you can see again here, I have MMS, this is FGM is the instrument, and then we have these data products. The data here is provided in a range of different coordinate systems. So there's body-centered, D-spun major principal axis, and these two geophysical systems. Again, we have some hyperlinks here, so you can go out and look at the documentation to kind of read more about the coordinate systems and how they're defined. These first two are MMS-specific systems. The body-centered system rotates with the spacecraft. So does MPA, which we're not using here. That's the major principal axis. And DMPA is a D-spun system. And so the x-axis for that points loosely towards the sun. Our D-spun system for MMS should be close to GSE, but we can use that as a sanity check, not for scientific analysis because it's not that close, but we can use it as a sanity check. So, let's do that. We'll set our magnetic field variable here to use B, that's the magnetic field, in DMPA, survey mode, which means it's sampled at lower resolution. And let's just look at what metadata we have for this to tell us, so it'll tell us about it. So it's 8 or 16 samples per second. It's stored as a 4-element array, which is X, Y, Z, and B total. So that's a gotcha to watch out for. No taking, the norm of the array and, that'll, unless you drop the total off first. Okay. So, and it has, because this is the ISTP standard, it'll give you like what your different SI conversions and things should be. So, and I am losing my place here, right? So again, let's take the time out of this, and because like I said, this is a lazy load. So this is now grabbing the data from the fields file, and it's stuffing the time from the MEC file and the fields file each into TikToks. And I'm going to be getting and storing in this TT variable the TAI time. So that's basically second since sometime in 1958. And that time scale does not include leap seconds, so it's a continuous series. Okay, and it's important to note that that's one of the drawbacks with your standard Python date times. It's not just precision, although they're microsecond accurate. They are not leap second aware. And so this all is. So what we're going to do, just for the purposes of this, we're going to say, look, survey mode, we'll just do a linear interpolation on the samples to get the data at the times in our MEC file. Says that this is 30 millisecond cadence that, oh yeah. So there's two different products for everything on MMS. There's survey mode, which has a lower cadence, and burst mode, which has a higher cadence. This is looking at the survey mode, just for reasons, I guess. Let's interpolate that, as I said, onto the MEC timestamps. we're using NumPy interp here, and we have an interpolation routine in the toolbox as well. There are some additional things that handles that traditionally were not handled in NumPy's interpolation. So it handles dates. We handled kind of wrapping at a certain value. So yeah, NumPy's interpolation handles that now. But initially, you know, if you had something that wrapped around, say, degrees or hours, toolbox would handle that. So it's just a little more, it's NumPy interpolation with a little extra handling on top. So let's plot some of this, and then I'll hand it back over to John. So just to prove that actually this works, let's close the CDF file, and then we'll just make this plot and throw on there the magnetic field values. Okay, so this is what that looks like. And at the top, I imported SpacePy's plot styles. And so this is the default plot style. It's going to look similar to some of the plot styles that are now available through Seaborn or Matplotlib. It is different. We have a different color cycler, which is chosen for colorblind friendliness. We have much larger default font sizes. You know, anyway, so again, we can do the quaternion math. I'll let you go through this, you know, in your own time if this is something that's interesting to you. But this is, again, just a rotation from our dspun to GSM. And what we're going to do now is basically just put them side by side, you know, give it that visual test. And so, you know, there's a couple things in here. I'm going to use on one of the plots, I'm going to use auto format xdate from Matplotlib. And on the other plot, I'm going to use SpacePy. So splot is SpacePy.plot. And we have apply smart time ticks. And what this is going to do is you hand it the axis, you hand it your time limits. And it's going to try a little harder to just say, how should this be represented? Okay, so you can see here that SpacePy has decided that actually we just want to go, you know, sort of here's the hour and minutes. And the Matplotlib built-in, it gives you more ticks. It also has this floating 11, which I guess is the day. You know, your choice. So then this comes to the question that was asked yesterday: can we transform arbitrary vectors between coordinate systems? And the answer is a qualified yes. So I'm going to step through this with the quaternions. Okay, so first of all, I'm putting the caching back on for a little extra speed. So then what I'm going to do is I'm going to rotate I'm going to use the quaternions to get my fields in ECI. And then I'm going to use SpacePy's coordinates to rotate my field vectors. Okay. And so then there's some plotting. And so you can see here again, like, you know, the left is using the quaternions to do everything. The right is using the coordinates to go from ECI to GSM. And the reason for this is that we mostly use position vectors, just like AstroPy in that discussion yesterday, because coordinates was really designed to work with position vectors. Most of the time you can put arbitrary vectors in there and transform between them. There are some places that won't work. So if you had something like ENU, so that's east, north, up, or for ground-based magnetometers, they like to use a variant, which is north, east, down. These are position-dependent transforms. And so where you are will change what the basis for that coordinate system is. There's a link here to a discussion on our GitHub, which kind of goes into a little more detail. Geodetic coordinates, that also applies to those because you use an ellipsoid for the Earth, and so locally vertical is not radially outward. So again, that's position dependent. We may actually end up using supporting some common use cases for this in a future version of SpacePy. And then the last thing, because I'm about a minute over where I wanted to be, is interoperability. So the last thing here, let's say we want to look at a satellite. We have a special satellite tracking telescope. We're at Bear Mountain. It's on the roof of the cabin. There's lots of mosquitoes. So we're going to say, okay, look, telescopes usually have some kind of altitude azimuth mount, right? And altitude here is an elevation angle, not a height. And azimuth is an angle positive eastward of north. And so that tells you kind of how far around you have to skew your head. So modified from the AstroPy docs here, we'll import AstroPy units. I'm not using U because I have a personal aversion to using single letter variable names. And then I'm just going to import sky coords, this Earth location, as well as altitude azimuth. So I'm going to take MMS data in ECI, and I'm going to put some times on it. And then I'm going to export that to sky coord. And so what that'll actually do under the hood is this will convert to a common frame, which is actually what in AstroPy is called ITRF. In SpacePy, that's geo. They're the same thing. And then we find where Bear Mountain is. We can look this, we can just put this in with an Earth location, give it a UTC offset. And then we can transform to altitude azimuth. Bang. So it's going to be about 20 degrees above the horizon, and it's going to be looking off roughly to the west. So we should be able to see MMS with that special telescope. Okay, so that's this rather contrived notebook. There's nothing in here that's MMS specific really, except the data. The whole point, as John said, of SpacePy, we don't target missions, we don't target specific data products, we target generic tools. And so because interoperability is important and is improving constantly, use the best tool for each job. Build on top of the ecosystem, and hopefully you can mix and match between packages. So are there questions before I kick it back to John?
Yep. So Steve, there was a question about comparing the transformation error early on to the position error bar, if that's represented in the Spice kernel or if it's in the MEC file somehow.
Hang on, is that question's in the Slack, right?
It is in the Slack, yes. Yeah, so you can read it rather than relying on my translation.
Let me look at the wording here for the interplay. Oh, hang on. Position error bar from Spice kernel. So we actually don't support Spice kernels, and actually MMS under the hood also does not use Spice. So that is a difficult question. I mean, I guess on the easy answer is not through SpacePy. I don't know how you would get the Spice kernels for this. If you had, say, Van Allen probes, that uses Spice for some of the positioning, and so you could use Spice to get the position error there. But yeah, SpacePy doesn't support that. Now I also see one here from John Vandergriff. Was that answered already?
Yeah, the others I've answered, but please feel free to jump into the threads and provide more context.
Okay, and okay. All right. Well, I think everything else looks like it was answered, and so yeah, I'll be on the Slack and I'll be back on here later. Okay, are you up next, John?
I am. Let me.
With something more interesting.
Oh, I'm not sure about that. So let's get that going. So the first question is if my screen is visible, and then the second question is whether it's large enough to be seen by people.
Yes and no.
Okay, you want that zoomed in a bit?
Yes, please.
I don't have a gigantic ultra-wide monitor. Is that a little better?
A little, just a little more would be great though.
How's that?
That's better. Can you minimize the sidebar?
I was gonna open my notebook first and then minimize the sidebar.
Oh, well, that's fair.
Alrighty. So again, doing the open with notebook to make sure this gets handed off to notebook instead of a text editor. And then we'll minimize that sidebar. All right. So the good thing is Steve has explained a bunch of this.
Sorry.
Gosh darn it. How small of a projector do you guys have running there? Is that a little better?
Yeah, I think that's better. Thanks.
All right. So Steve has explained what's going on where we have a shared SpacePy directory for you to be using. So that's all that this is setting up. It's also setting up just a reference to the data we have sitting there. All right. So this is work that came out of my thesis looking at energetic ions in the cusp of the magnetosphere and how that connects out to the tail region. And so that really relates very heavily to the magnetic field geometry. And so I thought it would be fun, rather than drawing a cartoon once, going and doing a bunch of stuff with our field model support, using a sledgehammer to kill a flea. I guess I've got one question is, I've got a bit of a black box down the lower right-hand corner that's obscuring some of my stuff. Is that also affecting your view?
Not that we can see.
Awesome. Okay. So if anything critical disappears in the lower right, let me know and I'll shuffle it around.
Sounds good.
All right. So I'm going to go and start this running. But basically what I want to do is get a rendering of the geomagnetic field using one of the Sync models, just so you can see kind of the global structure. And so we have the get B field function that ultimately calls down into the URBM library, and the positions come as the coordinate objects that Steve showed, and the time is the TikToks, which he also mentioned. And chords basically assumes you've got a whole list of XYZ positions, but it's kind of more fun to plot it as a 2D grid for given XZ. And so we'll show some of the transforms to that. The external field models depend on the solar wind conditions. So the Omni module is a way of taking that. Again, the data are stored in the shared SpacePy directory here and can be updated. The Omni module does the interpolation, and we go and do some of the coordinate conversions. So doing here is just setting up a grid of 0.1 RE and XZ, doing some NumPy magic, which I'm just going to skip over, but the point here is to set that up so we have a Y of 0, and then flatten it out so that it's that one long array of XYZ, XYZ, XYZ. Thanks, Sean. And we're going to be doing some stuff based on the distance from the center of the Earth later, which, just spoiler, it's because a magnetic field model doesn't work very well below the surface of the Earth. So we're going to be taking that stuff out. And we're going to define those as our X and Z coordinates in GSE. If you're interested in playing around with this, feel free to edit this to try SM or GSM and then run things again. You can kind of see how it comes out. All right, so we're setting up a coordinates object. Any transforms we do this coordinates object, we're actually suggesting to use that new Python-based backend. Again, that default will change. There's also, in the documentation, which we link heavily through here, you can set that default on a per module basis instead of each time you call. And I'm just choosing an arbitrary time. Those who are paranoid will recognize that I'm actually choosing a time with a low dipole tilt, just to keep that simple. And I'm going for all of those locations that, again, is a grid I flattened out, going and getting the Signenko 96 model field from that. And this gets returned as a dictionary where you have a magnitude and then the full vector. And that is in Geo. as Steve has pointed out, you have to be careful to make sure that you can do a conversion that's not velocity dependent. In this case, yep, it's a simple rotation. So we can take that geo and rotate it back into the GSE that we had before. And as I mentioned, anything below the surface, we're not assuming we have an external field model that's accurate. And then going and turning this into a big X to Z grid. All right, so this is just setting up a couple of arrays that we're going to actually do fun stuff with in a bit. So again, I'll run that. So I'm pulling things with Matplotlib. We're setting up as a color, and then pcolorMesh basically lets us do our color as a function of two variables. The transpose here is basically because I tend to think in terms of x comma y. A lot of the Matplotlib functions thinks of it in terms of row comma column, and so you will often wind up having to go and transpose your axes depending on what you're working with. And I'm just specifying some minimum maximum values. We make circles circular, otherwise things wind up being weird. And there's this little thing from the PyBats, which is basically space weather model support, to give you your little planet. So up to this point, what we've done is we've got this background color of the intensity of the magnetic field in the XZ plane, and we have an Earth. And then we get our direction as a simple unit vector, and then we call quiver in Matplotlib. That goes and gives us the direction of all of those. So this gives us kind of a rough idea of what that magnetic field is looking like on this day. Again, feel free to play around. I've got a couple of try things in here, so you could look at this in linear. You can look at having more arrows if you would like. So for instance, fewer or more. Play around with that. So this gives us a rough idea, but it'd be nice to actually see the field lines because that's the cartoons we deal with. And this is part of PyBats, which is mainly meant for supporting model output from the space weather modeling framework. And Dan will go into this in a lot of detail. But most of what we're doing is just starting off, looping over a latitude to try to launch some field lines from the North Pole and from the South Pole. Doing the trace through the fields, this is the key. This, given remember we have an X by Z array of the field, and then what we get back is a list of X and Z locations. And then again, for each latitude, we're getting that list of locations, we're plotting it out. So you can see out there, you can see very clearly the stretch in the tail, the compression on the day side. It is all fairly as expected. So one other little thing I like to throw on here is just, okay, so this is a magnetic field model. It's just an empirical model of the Earth's magnetic field. So where do we think the magnetopause is? And again, we have a built-in Shua magnetopause. And because that is rotationally symmetric, basically we're treating the XY plane and the XZ plane as the same. And so we get a location as basically, again, a list of positions, and then we'll go and plot it out. So we can see here pretty clearly that this is within the right domain. We're almost entirely inside the magnetopause. There's just little corners here. And as I said, you can of course see the compression on the day side, you can see the stretch on the tail, but it's always nice to be able to actually, label stuff. Matplotlib gives you a lot of stuff for this, but just, we can say, okay, you can see the cusp up here where things are opening up and exposed to solar wind, and then the tail here. So we don't have the bow shock model in at this point, but that's something that's probably going to be added quite soon. And then it would be the same way. We have the Shua magnetopause model. We have a couple of PlasmaPy models. And so two things that are kind of on my plate is to have those, well, first add the bow shock and then also have them kind of play in a very similar way. And I see Steve is typing, so he'll probably correct me as well. All right. So this just gives you a bit of an idea of what's going on. And I just want to point out that because we are in a fairly memory constrained environment in these VMs, normally if you're in a function and you run off the end of the function, stuff gets garbage collected for you. If you quit, stuff gets garbage collected for you. In this case, because I'm still running along doing a bunch of stuff and there's a bunch of variables I don't need, I just delete them to free up a little memory. Most of the time you don't need to worry about memory management in Python, which is nice. Any other quick questions before I push on? All right. So the science question that's of interest here is the observations of energetic ions that were made up in the cusp region. And by energetic, I mean basically ring current energies tends to a few hundred of keV. And the big argument over this, fortunately, this argument's largely in the past, so hopefully I'm not uncorking unpleasant memories here, is a question of whether, okay, were these accelerated locally in the cusp? And then if so, can they escape out and contribute to the ring current? Were they potentially accelerated in the tail, then drifted to the day side, or accelerated at the bow shock? So I had a list of cusp crossings, energetic particle observations from an earlier study, and that's what I am doing to unfold this. One of the things that's nice about Python is this is not something where you have to give up everything you have to date. The earlier work I did on this was in IDL, and it's actually very easy to read in the IDL data. So get that started. It's literally, it's included in SciPy, and you basically get back a dictionary which has all of your variable names. Within that, I then just go and cast. These were as ones and zeros, again, for historical reasons. So cast those out to nice Booleans. And then I go and take the times, which are as year, month, day, and minute, and go into that. So this is, I'm sure you've seen this about 100 times in Python now, which is list comprehension, which is one of those nice little aspects of the language. And again, just to simplify the math, these are all in nice date time objects, but it was just easier to go and do everything in terms of total seconds since 1996, because that was when Polar was launched. And this is, again, a nice little thing that NumPy does. If you have a function that takes one thing in, but spits one thing out, you can have this vectorized method, which will then turn it into something which will work on an array. The specific mechanism that we'll be using to analyze this really works on list of times, as in there's a time when this happened, a time when this happened. And what we have here is a list of times, then a list of yes and no. And the thing that's beautiful about that is if you have a list of one thing and a list of true and false in NumPy, you can just apply that true-false array as an index. You get back a list of times. This is a list of times when Polar was in the cusp, list of times when Polar was in the cusp and observing those energetic particles. All right, so that's kind of the output. And what we're interested in then is comparing that to some other geomagnetic phenomena. So the two things are what are called geometric storms, which are intensifications in the ring current. So this is interesting in both directions, of course. If for some reason these energetic particles drift down and drive the ring current, we'd expect perhaps some association in that direction. But it's also if the ring current particles are drifting up into the cusp, we might see something there. So this is using a high-resolution DST index, which is basically equatorial magnetic field observed on the Earth. This is calculated normally as an hourly index by the World Data Center in Kyoto, but the USGS did a 1-minute version of it. And so that's what we're doing here. Basically, I have a pile of those CDF files sitting in our data directory. This is again a list comprehension, just open them all up as CDFs. And then this cat CDF function goes and takes these functions from, these variables from all of the CDFs and puts them together into one array. So that's what we have there. And just to sort of take a look at what this looks like, if we take our list of times, we take the DST, you can see a pretty classic moderate storm of about -80 nanotesla. So here's our onset, main phase, and recovery. Now this is the uncorrected DST. It's possible for the DST to be affected by that dayside compression that we saw earlier, which can obscure those details of the storm onset. So we have, again, built in SpacePy get DST star, which will return that pressure corrected DST, normally using the hourly Omni database. But again, we have this 1 minute DST. So we're going to kind of do this by hand, taking the 5 minute high resolution Omni data, again, going and reading the pressure and the times from there, finding stuff that is fill, and then using the NumPy interpolation to get the dynamic pressure from that 5 minute data on every single one of the 1 minute data points. In this case, in order to make the NumPy interpolation work nicely, we convert those times, which are date times, as Steve pointed out earlier, into TAI. You can certainly do this with other time bases if you like. And then with a dynamic pressure and the DSTs, you can get the DST star. And again, if you just take a look at the output there, you can see they're pretty close, but there's a little bit of correction, particularly where there's that enhancement just before the storm starts. All right. The identification of the storms from here, it's obviously fairly easy from a Mark 1 eyeball to say, hey, there's the onset. But we're not going to get too much into details. Suffice to say, Steve and I spent a lot of time clicking through data. If you find yourself in a situation where you don't think you can get stuff done with a machine learning approach and just need some eyeballs on it, there is this event clicker. I'm going to skip over this because we're not using it. So what we're particularly interested in is, given those storm onsets that we've identified, does it look like we got storms? And so what we are doing is looking at that pressure-corrected DST as it varies on either side of that storm onset. All right, so this is the superposed epoch analysis module. So we take all of our time series of DST star and basically shift it all to those onsets and basically layer on top of every single storm. And so we can see that, yep, we've probably identified something that looks reasonably like a storm. Here's our interquartile range for the DST. The red dashed line is the mean, and the black there is the median. All right. I'm going to press onward. So this is looking at the geometric storms, those sort of long-term enhancements in the ring current. The other thing that we're interested in is substorm onsets, which again, I'm going to try to avoid the controversial angle here. Let's just say that substorms are not necessarily directly related to storms, but we have a list of onset times from earlier work. Again, this is an IDL. So I'm pulling it all in and just getting those times when that dipolarization starts, where that stretched out tail configuration starts to come in. Since we're short on time, I'm not going to go into too much detail, but we've got 4,000 different ones there. Okay, so here's where things get interesting. We've got a list of times when polar was in the cusp, for instance, or when polar observed interject particles. And we want to relate that to a list of times when either there was a storm onset or a substorm onset as measured by dipolarization. And one mechanism for doing this is called association analysis, where we look at the sort of the naive way would be, okay, take, say, all the observations of customer inject particles, and is there a direct lineup of a substorm onset, say, at the same time? Obviously, you're not going to get things directly lined up, so kind of the next step is to start thinking in terms of, well, what if you open up a little bit of a window around each of those and say, okay, if it falls within that window, then we think those are associated. So for instance, we have, in this case, one, again, call it a SEP observation. There's our half window, and maybe 2 dipolarizations would happen within that time. So that's a 2, 1 line up here, nothing lines up here. So these individual associations are not symmetric with respect to which series around you put, but if you add these all up, the association number is the same. So that association number gives you an idea of how closely these are related. The next thing to do is to start saying, well, maybe there's some time lag. So you slide one series with respect to another. See how that changes things. In this case, it decreases the association. And because we have computers and they're fantastic, you can imagine doing this for a whole bunch of different times and getting a whole long time series of, well, okay, offset by 5 minutes, offset by 10 minutes. And this is the essence of association analysis. So we are going to do this for plus or minus 3 days for our legs at a 5-minute resolution. And that half window that I'm using is 30 minutes. And the reason for that is because at the energies that of interest here, it takes, in very rough terms, about half an hour to gradient curvature drift from the tail to the day side. So that's kind of what we expect to be the slop. So if we look at this, this is as a function of the time lag, the association, again, between substorms, substorm onsets, and customer inject particle observations. And you can see that at lower legs, there appears to be some amount of association. Now, the idea is that even if these things are related in some way, if you move out to very, very large times, any association is broken, right? You would expect a dipolarization would not potentially be directly associated with a given interject particle observation a year later. So we kind of use this asymptotic region as an idea of what's the chance association. And so that's what that red line is. That's kind of the median out in this high leg area. But this doesn't give you an idea of whether this is significant. So the bootstrap is the next step of this, where we go back to the series of events, and we do this entire analysis of time shift over a whole range of times using a resampling of each of these series. And that's a resample with replacement. So if we have 100 times here, we will choose 100 surrogates from that, but we might choose the same one twice or 3 times or something. There is linked from this, there is a tech report that Steve and I wrote up kind of explaining all of this, including the links to the statisticians who actually demonstrated this is any good. But, so if we do that bootstrapping, looking for a 95% confidence interval, and then go and plot this again, we get some idea of, okay, maybe this association at short legs is actually real. But again, note I'm talking about customer energetic particles with the substorms, and we're leaving out the fact that during a substorm, we're reconfiguring the geomagnetic field. Maybe that's moving things around. It means polar is more likely to be in the cusp. And so if we do that same association instead with the energetic particles, just with the cusp crossings, we'll get back something similar. Apologies, I should have started writing that sooner. And so what becomes interesting is not so much whether there's an association here, but whether this energetic particle association is stronger than the association just with the cusp. All right. And so we have support in the POPI module for that, which gives you, this is normalizing to that cusp, that's the red, and so any place where that red and the blue are coming apart, you get an idea, you can start to guess that there's something significant. And so there's something right here we're running this with fewer surrogates for the bootstrap, just for speed here. If you run this with enough, there's a little bit opening up. So there's a slight suggestion there. Doing really basically the same thing with the storm onsets. You can see there's really no association there. So what comes out of this is that, yeah, there's possibly an association, but that's going to be in the positive direction of we're seeing those dipolarizations a few hours before we see the energetic particle in the cusp. So that kind of supports that particular energization mechanism. So this is, I want to use this actual science question to show you folks a few things that the coordinate conversions, which Steve delved into much more, that magnetic field, some of that plotting, and these superposed epoch and association analysis techniques, which are quite powerful. If you can think of anything in terms of a series of events happening and you want to have see if two are related, this is a really great way to do that. So I think we are up to the break if folks don't have other questions. Alrighty, sweet. So I think those of you physically present can, oh, you know, I never started my video back up. I am sorry. I'm sure I'm less interesting than the.
That's no worries, no worries.
Yep. Yeah, so you folks can go for your break and we'll see you at quarter till.
Sounds good. See you all at quarter till. Everyone who's here in person, we're going to go take a group photo. Let's see, what were Arno's instructions? So when exiting at the back of the room, exit through the emergency door and climb up the stairs, and we're all going to take a big group photo together. Okay. What's everyone? Hey, SpacePy, you all there?
I'm here. Does that count? This is Dan.
You are a rep, you count.
All
That's all
right.
that matters right now.
Let me share my screen and we can start by y'all letting me know if that is an appropriate shape and size.
I think so.
Okay.
It looks good from my end. Sean has the YouTube up. Let me see if it looks good there too. I think it's good.
Excellent. Okay. In which case, welcome back, everybody. Hopefully you were able to grab some espresso. We're now going to switch gears to talking about how SpacePy handles output from the space weather modeling framework. So very quickly, the space weather modeling framework is one of the major kind of MHD class models used in the community. Specifically, the framework allows you to take many different independently created codes, for example, of code of the ring current, the ionosphere, the plasmasphere, ionospheric outflow, and an MHD code, and connect them all together to create a synchronized and self-consistent simulation of the system of the magnetosphere, ionosphere, and thermosphere. So while that sounds great, and I should point out real quick, we'll just go over here. The SWMF is open source. A good chunk of it, I should say, is open source. So I encourage people to grab and play with it. It's a fun code to run if you like that kind of thing. The problem is that when you're connecting otherwise independently developed models of different parts of geospace, you wind up with a plethora of different output types, formats, data, and PyBats, the SpacePy submodule for handling the SWMF, is a module dedicated to trying to give you access in Python to all of those different data output types. And then on top of that, we can make some cool plots, do some analysis, and there are a lot of helper tools and functions to deal with that. So today, what I've done for this tutorial is in the files, and I'm just going to embiggen this a little bit. In the tutorial data, you'll notice that there are two SWMF folders, one entitled SSI North, or Storm Sudden Impulse for a northward IMF BZ case, and SSI South, one for a southward IMF case. And our goal is to take this paper by Wheeling et al. I don't know who this guy is. It's probably not a worthwhile paper. But to reproduce some plots from this paper where a example extreme coronal mass ejection was constructed rather crudely, I might add, with a step function like in the solar wind velocity and density, and with IMF BZ profiles that are either purely northward and purely southward. So we have two simulations, and we want to explore the output, figure out what's in the different data files, use those outputs to illustrate the magnetosphere ionosphere response to this extreme CME. So we want to reproduce specifically, this is figure 2 from the paper. And when I get a chance, I'll drop a link. There's links in the notebooks to this paper, but I'll drop it in Slack as well. But each row here is a different point in time as the CME impacts and passes the magnetosphere, for the northward case on the left and the southward case on the right. And then we want to get quantitative and create this plot that shows the DST response of the simulations and then the standoff distance of the magnetopause below. So let's go to our Jupyter notebook here and dig in. I'm going to hide my files. Actually, before I hide my files, I want to point out that these directories are organized in the same way that SWMF output is organized after you run the code and grab all the files together. So I really wanted to make this a real world type tutorial. You have a single folder for each code that was used given a 2-letter code. So GM is the global magnetosphere, it's your MHD results. IE is your ionospheric electrodynamics, etc. Now, in our GM folder, you'll notice we have 2 files. And I'm going to make this even wider for just a moment. We'll go back to the tutorial in a second. We have a log file, which is a simple ASCII time series of both diagnostic data, like average pressure in the run, as well as DST and a couple other values. And this really long named file that is a series of y equals 0 plane cuts through the MHD code. And you'll notice the extension on this file is .outs. So this is a binary file originally made to work with IDL. It's a format proprietary to the SWMF and BATS-RUS. I mean, it's kind of a basic Fortran dump. You should have, I see someone says we don't have these files. They should be in the shared directory. Oh, a lot of people don't see them. Okay. I will work on fixing that when I'm done talking through this. If anybody else could jump in and try to help out with that. They should be in the same directory as all the other SpacePy data under the JT Niehoff SpacePy tutorial folder. So there's 2 file extensions we need to worry about from the, well, a lot more than 2, but 2 big ones we want to worry about. One is .out. That is a single slice or a single output dump for a single time, and .outs with an S, which is a series of files all concatenated together. And these can become very, very large. This is a format that's common to a lot of the models. So we have tools for reading that and navigating those. And then in our IE directories, we have a bunch of gzipped ASCII files that are non-trivial to read because of very lengthy headers. And those contain our 2D ionospheric electrodynamics, each at a different point in time. So moving back here, our first step is to just read these files. And actually, let me back up here a little bit and just point out we have the same kind of commands up here just to kind of initialize our environment that Steve and John used. And then we're going to import our libraries. And there's a whole bunch of discussion in Slack about finding the files. Sorry about that. I am going to unpickle some data later in this tutorial as a convenient way of skipping some steps. We're going to import NumPy, Matplotlib. We're going to use SpacePy's plot module, which has a lot of convenience and style functions. Matplotlib grid spec. If you've never used Matplotlib's grid spec functionality, it's really cool. I strongly suggest it. And then from the PyBats module, we're going to import PyBats itself, the top level SWMF handling module. And this contains methods and objects and classes that are generic to the SWMF and anything that's useful for more than one model. And because our simulations use both BATS-RUS and the Ridley Ionosphere model, RIM, we're going to import 2 submodules, BATS and RIM. So now let's go ahead and dive into these files and figure out what's going on. The first thing, and oops, I need to run. To slow myself down. I'm not typing these, but I am running these cells. So I want to make sure that I'm doing that. So in this first cell here, all we're doing is setting a couple of convenience variables pointing at the 2 directories, the directory containing the northward IMF related files and the southward IMF file. And then we're going to use 2 classes to read some of the data that was in the GM folder. The generic log file class is just for opening up a basic log file that's time series ASCII. So path north plus the location of the file. And then the same thing for the .outs file. But now we're going to use this generic IDL file class, and this will read either a binary or an ASCII formatted IDL.out file. Okay, so now that we have these two objects, log and MHD, how do we know what's in them? And because they are built on the SpacePy data model objects, everything works exactly like we'd expect before. So let's go ahead and run this cell. Give it a second to read that data. We have top level attributes, and you can see sometimes there's a lot of information in these files. Specifically for .outs files, you'll see that there is run times and times, which are arrays telling us all the times at which we have output in this file. We have the without an S time down here, and runtime, and let's see here. Lost the other one. Where's my frame? We'll get to that eventually. But telling us of all those frames, all those snapshots from the MHD code saved in this file, it's telling us what one's loaded now, because we don't want to load all of them at once. Sometimes these files are like multiple gigabytes and we don't want to use up that much memory. Same thing with the log file. We have a lot fewer attributes. The two objects inherit from dictionaries, so we can do mhd.keys, and the key value pairs are our actual data values. So for example, in our MHD object, we have X, Y, row, UX, BX, etc. You know, the standard MHD state variables plus current. And we can use the .tree method that Steve Morley pointed out to get more information about what's in there, including the variable attributes as well. An example of the variable attributes here, we can just, you know, if I look at the attributes associated with P, which is the pressure value, we see, you know, we have units associated with it. And then for, if I want to get any of these values, it's that same dictionary syntax, that key value pair, where when I run this cell, the DST value inside my log file object is an array of DST values for this simulation. So here I already covered the difference between the out and outs files via, you know, one is just one snapshot of the data at one point, and the outs is many of those concatenated together. Let's see here. It looks like people are still struggling with the finding the files. My apologies for that. But here, this little print statement, it just shows us how we can figure out in this outs file with many separate frames what one is currently loaded. When I type MHD P to look at the pressure values, you know, what time is that associated with? So here I used a clever little F string. If you're not using F strings in Python, you are missing out. I promise you, it's really cool to say that there are n frame number of frames in this file, and we can see the times as well. So I will execute that cell, and we see there's 4 frames in this file. We can see the date and time associated with each of them. Conveniently, those are the 4 times that we're going to plot here shortly. I can also look at what frame is currently loaded by looking at the iframe attribute and looking at the time attribute to get the current time that's loaded in the data frame. We're currently looking at frame 0. So remember, we're Python, so we're 0-based indexing. There's 4 frames in this file, 0, 1, 2, 3. If I want to switch from frame to frame, I use the switch frame method. If I need to get output for specific events, how do I download the associated data? So this is the big challenge with the SWMF, is that if you didn't run the simulation yourself, you need to find somebody who did run the simulation. I actually have some data I'd be willing to share with you all. Actually, if you look at I'm not sure how much of it is shared via this paper, But in a lot of my papers, you can look at the acknowledgements and see links to deep repositories to grab the data from a certain simulation. I have simulations that I'm willing to share the data for. Simulations run at CCMC. They will process and create different output types that aren't covered in SpacePy, so heads up with that. But a lot of times they will share raw data as well. So switching frames, the switch frame method allows us to go from one snapshot to another in the same file. So mhd.switchframe3 is going to take us to the final frame in the file, currently loaded as frame number 3 at this time. So far, in just kind of rolling through this, the two classes that we used in this demonstration are, let's see, right here, this pybats.log file and pybats.idl file. And these are very basic classes meant more than anything to just give you access to the data in Python. But the real trick with pybats is finding the most specific class for the specific data file you have, because that's where you're going to find the plotting methodologies. That's where you're going to find extra calculations and more useful tools. So recognizing that this file is a y equals 0 2D cut through our 3D MHD data, output data, I'm going to use this bats.bats2D class. It's going to inherit from IDL file, but have a whole bunch of more cool tools associated with it. So here you see we load the data in much the same way, but now we're using this more specific class. And if, let's just real quick, I'm just going to comment out these two lines real quick. And I'm going to run this cell for a second, and it's going to open that file. And if I do mhd dot and I hit tab, oh, it's not going to let me load this because it doesn't recognize. Let me insert a cell real quick. Insert. Oh, look there, it popped up finally. It's just slow. You see how many object methods there are associated with this. There's a whole bunch of calculations, plotting methods, stream tracing methods that aren't available in the base class. So let's go ahead and close that. And I'm going to call a method called calcb. That's going to calculate the total magnetic field, bx squared plus by squared plus bc squared, take the square root of that, and also calculates the unit vector. And what this will do in the end is create a new variable called bx hat, which is the x component of the b unit vector. And there's a whole bunch of stuff like that, Alfvén speeds and whatever. And if you are looking for a calculation that you think is pretty standard that's not there, put in a feature request and we'll be really happy to add that. So as it turns out, the ionosphere data here, and I'm kind of jumping back and forth between Slack and my screen, my apologies. The ionosphere data is, those files, their format is unique to the Ridley ionosphere model. So we don't have a base class for that. So we're going to use the RIM submodule and the Iono class, and we're going to open up this guy and take a look at its innards using the .tree statement. So even though the files have really different information in them and different formats, when we open them, they all behave the same. And so just like Steve and John showed, we can navigate through these objects pretty easily. Overall, kind of the golden rule when you're using pybats is the more specific an object you can find for an output file you have, the more useful stuff's going to be in there. And so if you're looking at, for example, output from the polar wind outflow model, if you don't see a class specific for your output type, then in the .pwam module, then you want to roll back to pybats. And if it's still not there, then complain to us. And if enough people complain, we'll work on it. Right now we have people, Alex Glosser at Goddard is working on expanding the pwam module tremendously. And we have a branch with a much more featured SIMI ring current module in there as well. And we're always trying to add more. So now let's talk about making plots with these output files. And here you're going to see that almost all of the plotting routines are object methods that begin with add underscore plot type. And what we're going to do, I'm going to comment out this line down here in this cell, and I'm going to run this cell. I'm going to run this little method called mhd.addGridPlot. And it's going to return a figure and an axes object, a matplotlib figure and axes object. And we're going to get a brand new figure, a brand new axes, and this is a nice little canned plot to show us the grid resolution being used in the MHD code throughout the whole domain. And everything's labeled and it looks great and everybody loves it, right? Fantastic. So now what I'm going to do is I'm going to go ahead and I'm going to comment out this little part here. And I'm going to use the add contour function, or object method, I should say, to plot pressure as a function of X and Z locations in the equatorial plane. I'm going to use 21 contours on a log scale. And I'm going to see a second plot here. Wow, isn't that fantastic? We see the Earth, we see pressure contours. This big bright line is our CME shock wave coming in. But what I'm noticing here is, what are these weird steps in my CME and this pressure? This is really crazy. This doesn't look physical. What's going on here? I wonder if it is associated with grid resolution. That's a really good hypothesis that I could test by plotting these contours over this grid plot. And that's actually pretty easy to do thanks to this add target, or excuse me, set target syntax we have in SpacePy's plot module. Long story short, almost all of these plotting functions have two extra keyword arguments, target and loc, L-O-C, and we'll see loc in a second. But target allows us to specify where to put that plot, either on a specific figure or a specific axis. So here, I uncommented the back half here, and I am going to plot. So when I run this guy, I get my axes object back. And when I execute my contour plot line, I'm telling it to put that contour plot on the axes that was already made. And then I'm turning my contours from filled to just line contours so we can see stuff. Now it plots my contour on top of my grid plot. And wouldn't you know it, when you have really low resolution, you can't resolve very steep gradients. MHD is a wonderful thing. This actually isn't a big deal for these runs because what we actually care about is all in this high resolution region. We're really not worried about the deep tail or the far flanks. So setting the resolution low away from the core region helps us make these runs a lot faster when we're running them on Pleiades or whatever supercomputer you want. So this next chunk of code down here is very similar, but now I want to look at the magnetosphere and the ionosphere in two axes on one figure. So I'm going to start, my first line here creates my figure object with 8 inches by 4 inches because that looked nice. And then I'm going to call my add contour method again. But this time plotting pressure on a log scale. I'm adding a color bar. Could you please tell a bit more about grid stretching, how you did it? That really gets into running Bats R Us itself. I'll respond to that one in chat when we get to that spot. When I'm done with this tutorial to explain that. Essentially with Bats R Us, you configure the grid at the beginning of the code, and then you can allow it to change automatically or remain static. So it's not necessarily stretching, but the block tree, each block in the block tree has a different resolution. It's cool stuff for sure. And then these last two keywords are going to zoom in on my plot. Like I don't need to see like the whole domain of this giant 256 by 256 by 256 RE simulation. I just want to zoom in a bit. My target is the figure I just made. And then this loc keyword will create, if I don't specify an explicit axes, it's doing the same thing as add subplot in matplotlib. It's going to create a 1 row by 2 column set of subplots and return the axes associated with the first of the 2. So I'm going to comment out of this line for just one moment. And then down here, I'm going to add a contour of field align current from my ionosphere object, add a color bar, put it on the same figure, but now pick, use the loc to separate to set the neighboring axes. And when I run this guy, there we go. We have our little side-by-side plot where we can see both the magnetosphere and the ionosphere. Fantastic. Now let's go ahead and uncomment this line, which is add B magsphere. And notice I use my target keyword again to put it on the axes that was created when I made my contour. And what this is a nice little shortcut to add magnetic field lines. It actually does the field line tracing through the vector field and everything. It's cool stuff. Unfortunately, I'm not going to have much time to do streamline tracing. Suffice to say, there are a lot of useful helper functions for extracting and plotting streamlines, both of any vector field contained within your MHD code in 2D, and we're working on that for 3D now. Okay, at this point, we have all of the components we need to make this plot. So this huge bit of code in the notebook that follows what we're doing is the code I used to make that figure. And I know you're probably looking at this being like, oh my gosh, what is this? This is way too much. Well, let me tell you, the secret here is that probably about 60 to 70% of this code is polishing. It's setting the axes labels. It's making sure things don't overlap and things like that. So for those of you who are really new to scientific programming, when you're making complicated plots with complicated layouts, I recommend drawing on paper what you want and where you want it to get a rough idea, and then creating a script that allows you to iterate, because most of the work is polishing and getting things exactly where you want. A couple of things to highlight. One, because I know that all my plot commands for my MHD contour plots are going to have very similar keyword arguments, I group those up in dictionaries to save myself not only a lot of typing, but also if I decide, oh, actually I want the Y limit to be a little bit bigger, I change it once instead of 5 times in the code later. We're going to start by opening the MHD files, just like we did before, but now for both the northward and southward IMF cases. I'm going to grab the start time by looking at the attributes of one of my files. I'm going to create a figure, and this subplots adjust command sets all my margins. This is like the last thing I do when I make a figure, but when I'm building a figure, I should say, is figure out exactly what all the sizing is. And then I'm going to use the grid spec functionality of matplotlib to help me get the effect of some plots are wider than others, right? My circular plots are square. My magnetosphere plots are wider. Grid spec is really cool. Then I'm going to loop over the frames in my .outs files, right? I'm going to start with the first time, then the second time, then the third time. And for each of those times, I'm going to plot my magnetospheres in a row. I'm going to open up my ionosphere files associated with those times and plot those, and then polish. So I'm looping over the number of frames. I'm switching frames in those output files, progressing from the first time to the second, etc. Getting the time from my attributes and using that to build file names to open, right? The file names, if you notice, are have the time that they were written, or the time within the event that they were written. So I know if I'm looking at 605 universal time in my MHD, I can find the corresponding ionosphere file. So we do that and we open up those files. This chunk of code is basically saying for all, for the two simulations, find the max and the min of the pressure and the field line currents to make sure I can set the scales so that they have the same contour scaling. And then I plot. I create my axes. I add my contours to those axes using that star quargs, takes that dictionary of keyword arguments and places it right into the arguments that I'm handing to the contour plot function. I add my magnetic field lines. I add my ionosphere field line current. Well, no, excuse me. Add my new axes for my ionosphere plots. Add my field line currents to those. And that's it. That's the fundamental of creating that plot. Everything else beyond this point is polishing, right? I'm using the position of the axes to determine exactly where I want to put my color bar and line things up. I'm doing that for these labels on the side, my title on the top, and I'm just kind of putting things where I want them based on the location of my axes objects. I'll let you read that. I put a lot of comments in there, so hopefully that part won't be anything too confusing to figure out. It's really just matplotlib manipulation. And then when you see how much code there is for polishing. When I run that, it's going to take a second to build that plot because we're tracing field lines, we're reading the MHD, we're flipping through those. But eventually we'll get our wonderfully beautiful plot. Oh, come on now. I believe you're going to show up. That'll pop up in a second. There it is. And it's almost the exact same plot that is in the publication. This is neat. This is actually I don't have time to explain this too much, but we can see the compression of the dayside magnetosphere for this extreme coronal mass ejection event. And we also see that for the southward IMF case, this column on the right-hand side, that reconnection is causing erosion of the magnetopause so that we get a much deeper compression for the southward case than the northward case. Our final task here is going to be to quantify that value. And what we want to do here is figure out the radial distance of the magnetopause. Now, there's a number of ways to do that. And there's ways to do that that are better than I'm going to show you now, but this one makes for a much more simpler tutorial. But let's do this for the southward IMF case. And what we do know for the southward IMF case is that if we know what the magnetic field is from the Earth-Sun line, the magnetopause is going to be in between that spot where the magnetic field of the Earth is still northward and the magnetic field, the IMF, is southward. So we want to find that transition from positive to negative in the Z direction in the magnetic field. To do this, what we're going to do is extract magnetic field, or all our values, from our 2D simulation data. And we're going to use a nice little function, object method, I should say, called extract. Essentially, this allows us to say for an arbitrary set of points, take all the values from our MHD code and interpolate them to those sets of points, and then we can manipulate and play with those. So that's what this code does here. We're going to switch our frame to the second to last frame. That's a pretty interesting point there. Radial distance. My apologies for that. So then what we're going to do is create with NumPy a series of points that are in the equatorial plane that go from 2 Earth radii out to 8 Earth radii with a separation of 1/16 Earth radii. Then this line here does the extraction. This is our MHD object, extract, gathers all the variables at the locations that we give it, and stores it again in a really nice self-contained SpacePy data model object. So with this line object, I can use adders, I can use my dictionary syntax to see what's in there. These next two lines use NumPy logical Boolean indexing or logical indexing to determine at this first line is, okay, what is the first point in my vector of points where BZ is less than 0? And it saves that location. And then we do the inverse. We find the point on the Sun-Earth line, the last point where BZ is positive. We average those two locations, and that gives us an estimate for our magnetopause boundary. Now, if we were really good at this, we would do a whole bunch of field line tracing and look for the last close, blah, 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 blah. But I didn't want to get that deep into it, into a tutorial where I only have 5 minutes left. These lines down here just go ahead and show that this algorithm works. We're going to create a figure in an axis. We're going to plot BZ as a function of X. We're going to add some labels because we're good at that. And then we're going to put a vertical line where our estimated boundary is. So when I do this, there's our plot. We see the Earth's dipole field falling off at a 1/r³ rate. Perfect. We see here in this very short distance, that's where reconnection is going to be happening. And this vertical line marks the point where IMF flips from northward to southward. And we're going to call that our magnetopause location for that point. Now, for the paper, we actually did this a different way in the paper. But for this exercise, if we had the entire simulation with, I think it was like 5-second output cadences and all that, we could find this boundary by looping over all the entries in our file and repeating this algorithm and saving it to an array. But I went ahead and did that offline and stored the results in a Python pickle that you can find in the tutorial data. So we're just going to open, this first bit of code here just loads the data from the pickle. It has the data both for the northward and southward case. Then we're going to open up our bats.rs log files because these contain DST. We're then going to plot, we're going to create a figure, and we're just going to create some really simple line plots. Actually, I'll show you exactly what we're doing. It's figure 3 here. We want to see DST for our northward case in blue and our southward case in orange. And then we want to see right below that our standoff distance, again here in blue and orange. And we can see, okay, at this point, the CME has hit the bow shock. We see the compression signature in DST. And then we see the erosion of the compression and the erosion of the bow shock of the magnetopause at a similar time frame there. So that's what this bit of code down here does. Again, plotting is simple. Polishing takes a lot of time. Here, I felt for some reason that maize and blue seemed a little more appropriate colors right now. But there, we were able to reproduce the plot from the paper, no problem, including our standoff distance in DST. So with that, that's kind of a really fast run through to give you a feel of how SpacePy.pybats works. The fundamental functionality is to get all this heterogeneous data that comes out of these simulations accessible to you in Python, and then add more layers of tools to make the analysis progressively easier. And everything, because it's built on SpacePy's data model package, behaves in roughly the same way as you manipulate and change things. So I have about a minute left. I don't see any new questions in Slack, but as those pop up for the rest of the day, I'll be happy to address those. Thank you. And that's all I have. So I think John is up next.
Actually, it's Steve for round 2.
Steve for round 2. Excellent. Thank you all.
Yes, everyone gets the pleasure of saying goodbye to Dan. Let's see, where is this? All right. So what we're going to be doing, so remember, as always, right click and then open as notebook. We're doing cutoff rigidities. I have tried to adjust the window size here, so maybe it's slightly less distorted. I guess we have some aspect ratio differences between my ultra wide monitor and the projector. Is this legible for folks?
It looks good on my screen, but I'm
Yes,
not
it looks
on the
good.
other
It
side of
looks
YouTube.
good.
So
Okay, perfect. So yeah, so this is going to be hopefully a slightly more interesting run through than the last one, which was really kind of, you know, like I said, a test suite in a notebook to kind of work through how coordinates work. This is following a similar theme to, say, John's earlier notebook or Dan's, where this is trying to follow something that was in a paper. And so this is looking at rigidity cutoffs. And so essentially, Earth's magnetic field shields us from high energy charged particles. For example, solar energetic particles or galactic cosmic rays. And so what we're going to look at here is inspired by this paper by Don Smart and Peggy Shea in 1993. We're going to look at their figure 2 and essentially conceptually get to that point and extend it somewhat. So if this is a topic you're interested in, go check that out. What does their figure 2 look like? It looks like this. You know, it is, you know, dated, but, you know, we have something where we have the constant that they're looking at as a function of time, and we see it decreasing. And this is their Sturmer equation constant. So that's what we're going to get to. We're also going to use this to use the opportunity to look at data from the Global Positioning System constellation, not the GPS timing and navigation, but energetic charged particle data, just to say that it's out there and also to illustrate yet another file type. So these are the kind of the main things we'll be looking at, you know, simple file retrieval, I hit that earlier. And it just like earlier, we're actually going to skip that. The data is locally on the HelioCloud server. Working with JSON-headed ASCII. What is JSON-headed ASCII? We'll get to that. Time system conversion. Again, you know, there are a couple of options here which are, as pointed out earlier, interoperable. So we're going to be taking also 1D data, putting this into 2D. So this is, you know, kind of flux as a function of time from different satellites, as a function of time and position. And we're going to be putting that into kind of a binned 2D presentation. We're also going to be using a convenience function called level plot to make a classic traffic light plot. If you haven't seen one of those, you will. If you have seen one, this is how we make them. And there's going to be a little bit of, you know, peer at this later in your own time, you know, just to look at building classes. It's not SpacePy specifically. It's more, you know, just figuring stuff out. So we're using, as before, leap second data, also geomagnetic index data. I think John mentioned the Omni module. That's how this is managed. For the summer school, again, we have this is PyHC equals true. So let's just set that. And then we have a cell here which does some additional setup. And so this is just to point to where the data for this tutorial is. You'll need to run this. There's also a little patch here because on the specific versions that we're using for the summer school, there's actually there's actually a bug that came up when the Matplotlib API changed. So this fixes that. If you're using something newer than the current release of SpacePy, so if you're working from the repository, this is fixed. If your Matplotlib is older than 3.5, this isn't a problem. So just for that very narrow overlap, this fixes everything. So we'll just run that cell and then do the imports that we need. We're using constants from SciPy. We're going to be getting some dates and some plotting from Matplotlib. And from SpacePy, we're using data model because that kind of underpins a lot of our data handling. I mentioned earlier in the coordinate systems that we have systems like, for example, GSM coordinates. That's geocentric, solar, magnetospheric, and that is a magnetic coordinate system. And so that needs Earth's magnetic field to be specified. So for that, we provide currently as a stripped down implementation, but it is an implementation of the IGRF, that's the International Geomagnetic Reference Field. And so we use that to get the location and orientation of Earth's dipole axes. And so we'll be using that here. There's the Omni module for that kind of data handling, SpacePy plot and SpacePy time. And then as we had earlier, and I think you saw some of this plotting in Dan's as well, we're going to set our SpacePy plot style to be just the default SpacePy style. So let's illustrate what we mean by geomagnetic shielding. And I'm going to use the GPS particle data for that. For this summer school, as I said, this is already in the tutorial data. That's in the shared directory that was that Dan was talking about earlier. So if you are running this off of HelioCloud, just uncomment this URL live request and line, and it will download the data for you. This is archived by NOAA. Okay, so let's just run that. And so what this gets us is this gets us JSON headed ASCII. And one of the common issues with ASCII formats is that you get this file, which is some kind of flat file that has a bunch of different columns in there. If the person that gave it to you is really good, maybe there'll be some sort of header that has column names, but it doesn't carry metadata in the same way that you would get from an HDF5 file, a NASA CDF file, a NetCDF, a FITS file, anything like that. So quite some time ago now, I'm thinking it was probably about 10-ish years, maybe a little more, there was a kind of a magnetospheric community effort to develop a self-describing ASCII format. And so this is essentially NASA CDF in a text file. So you can store metadata and ancillary data that's non-record varying, and that's stored in the header using JavaScript object notation. The reason we do this is because it's both machine readable and widely supported, but also human readable. And so what does that look like? It's in the header, so it's behind a comment field, and then everything is kind of delimited with these braces. We have metadata like the copyright, and you can think of this as essentially a key value pair, right? And so you look down here, well, where's the data from? Who should I contact about this? And so then there's metadata for all of the variables that are in there. There's, latitude, and it tells you this is one column and it starts in column 1. If we come down some more, there's a measured electron rate. And so this is per second, hertz. It has some convenient stuff here to help you plot it with automated tools like autoplot. And this starts in column 4. And these are pretty huge files. They get into just like flat looking ASCII down here. I'm just looking for the bottom of the header. Doesn't matter too much. So let me hide that now. So that's what that looks like. It's a way of having ASCII that carries metadata. And so we read those into the same format that, into the data model, the same as from CDF, from HDF5, that kind of thing. So it says read JSON headed ASCII, and my GPS file name up here, I have these braces in there so that I can just fill in whichever satellite number I want that'll read in the file. So I read all of my data in. As with all of the other convenience routines and data model, it's an all at once read. It's very greedy. So we then have the metadata. And as before, we can look at this using our tree method. I'm adding verbose is true, so I can see what the data types and their sizes are. And I'm also adding attributes is true. So that's these items with colons, so I can see where the metadata is. And this again follows the ISTP standard, although I'm not sure exactly how strict that is. Okay, so there's quite a lot in these files, as you can see. So we'll just scroll down, or you don't even have to run that cell. Okay, so timing. Now, there was a good discussion of time from AstroPy yesterday as well in terms, and they mentioned the concept of scales for time. Generally, we deal with stuff that's expressed in coordinated universal time, so UTC. There are various other scales. And so there's also time zones, and I like to ignore those. So UTC is not a continuous time scale with a constant number of seconds per day. There are leap seconds. It's not handled by date time. So a lot of things that need a continuous time scale and need to not worry about leap seconds use non-UTC timescales. And so things like TAI, which we've seen used a couple of times, and also GPS time. Now, these data files have the time in GPS time, and we want to convert that to UTC. So it provides, as you'll probably find in a lot of, either legacy files or files that were designed by legacy people, you'll see we have a year and we have a decimal day of year. So this is a fractional day of year. So in the SpacePy time module, we have a convenience routine that will get the day of year, which will take day of year and convert it to a date. And there's a bunch of different options here. You can get date time output or not, and that's what this is doing. And then there's also whether you want to handle just the integer day of year or whether you want floating point day of year. And so that's what this is, floating answer. So that's set that to true. And so then this will give us, for the first element of that array, the date and time. This doesn't take leap seconds into account. This is GPS time. And GPS time was defined as being the same as UTC at this particular time. So 96th day, that's fun. That 9 should be a 0. Anyway, it's the 6th of January, 1980. And so there was some number of leap seconds at that point already, but this is where it crossed over with UTC. So the way we want to get this into a time system we need to know, that we know about is we want to convert it to seconds from the GPS 0 epoch. And then once we have that, we can get this into other, into any package we want, like, SpacePy's time or AstroPy's time. So I made this function here, which will get you your times from the GPS data files, and it takes in the year and the decimal day, so that's the fractional day. And there's a little flag here for using AstroPy or not, and there's two different methods of doing this. So I've got some notes. The main thing that we do is we, first of all, we make sure our year is integer, then we convert to the day of year to a date. And then we take our 0 epoch and we calculate the offset in terms of total number of seconds. So then, depending on whether we're using SpacePy, we can just give it the number of GPS seconds and tell it that it's GPS seconds. Or we can grab AstroPy time And we can do the same thing here. We make a time with GPS seconds and have format equals GPS. GPS is not a separate time scale in AstroPy. It is a representation on the TAI scale because it is offset. And so that gives us, there's some little hiccups that you might hit with that. It is well implemented. It's just, the time system itself needs some thinking about. So let's just run this here. What do we get out of this? Ticks from GPS, give it some inputs, and just look at the first one. So we get a tick-tock back with this time. So this manages things internally as TAI, so everything gets converted to TAI, and then pushed back out. The representations that we have for our string outputs and datetime outputs are on the UTC scale. Everything is on the UTC scale when you get it back out. So let's print this in our ISO format. This is ISO 8601. And you can see we get something that's nice and compact, but it's actually missing the milliseconds that are here. So there's 8 milliseconds we're missing. So let's adjust the precision on that display. ISO format on this tick-tock object, we can set it to display the full microseconds. And there they are. They're there, they're just not shown in the ISO representation. For interoperability with AstroPy or SumPy, you may want to use AstroPy time. So trust but verify, as I was doing earlier. Let's set use AstroPy to true. And then we'll print this. And for because of reasons, I'm going to also print which scale this is on, okay? So you can see that these times are not the same. This is on the TAI scale, whereas this is on the UTC scale. So we just click in here. This gives us a little more information about it. There's this issue on AstroPy's GitHub where they give a good explanation of why they put GPS on the TAI scale instead of having GPS BA scale itself. Okay, but what we can do is we can copy this out. If we explicitly cast this to the UTC scale, it gives us the same answer. So we can also make the time directly by specifying this Astro APT data type. And so that will take a tick-tock. It will take an AstroPy time object and make a tick-tock from it. Okay, so what we're going to do is I'm going to actually, can I skip this? Sure. So I'm not going to copy that stuff in there. This will do the right thing. Because when we take this in, it will convert from the TAI scale and everything meshes nicely. I urge you to work through the answer box in order to confirm that. So let's look at this GPS proton data. I'm just making a single panel, plotting on a logarithmic y-axis, the time, and we want to specify this as UTC. And I'm just going to plot the 0th channel of proton integrated flux. Set a label, apply smart time ticks, and we've got a rather friendly looking large picture here, which has all of these little kind of periodic spikes in there. And that's because it's from a satellite that is whizzing around the Earth every 12 hours. And so it's looking at different things, okay? You can see here, Smart Time Ticks has decided this is a fairly large range. I'm just gonna give you the date and some minor ticks. This often gives something that you want to look at out of the box. Sometimes it needs a little TLC. It's smart, but it's not that smart. So, so then what we're going to do here is we're going to get into this spectrogram thing, and that's going to take this type of data from multiple, like from, in the end, multiple satellites. But rather than just plotting it as a function of time, we want to plot it as a function of time and L. And L, if you were to look in a dipole field, is the equatorial radius of the crossing point, like of the minimum in the magnetic field line. And so it kind of gives you a radial mapping of where that field line goes to. In a realistic magnetic field, it's a little more complicated than that, but it's approximately radial distance. Okay, so what this is doing, that is, let me, what I'm going to do here is I'm going to restart this kernel, because that is not what is supposed to happen. And then I will run all above and see if we hit this again. Is this actually running? There we go. When in doubt, restart the kernel. Okay, so you can see there's a warning here. This is something that will probably break in the future unless we fix it, so we're going to fix it. However, it's just a warning. Matplotlib doesn't like you mixing different formatter types, which I'm doing here. And so this is what that data that we were looking at, the time series, this is what it looks at as a function of date and L here on the vertical. And so what the color represents there is the flux, okay? And we've got this log scaled flux with our SEP event here and some interesting higher flux at low L there. And so that's what all of these spikes were. So there's some notes here. Basically, you know, bin sizes are automatically estimated if you don't specify them, if you don't set limits, so then it does it for you. This low L proton flux increase could be one of two things. It could be energetic electrons trapped at low L, or it could be energetic protons, I suppose, trapped at low L, or it could be contamination from the radiation belt, because, you know, it's an instrument and the radiation belts are a pretty harsh environment. So there are some approaches written in here on how to look at some of these things. So what I'm going to do is I'm actually just going to say, well, is this likely to be an enhanced radiation belt contaminating our instrument? And so I'm going to set, you know, start time and an end time. I'm going to make a 1 hour time delta. And then I'm going to use tick range to automatically expand this out into a TikTok object that has, you know, this this time range and this resolution. I'm going to use get omni to automatically grab the KP index for me. And then I'm going to use level plot to plot this in a what we call a traffic light format. So if you go to, for example, NOAA's Space Weather Prediction Center, you'll see things like this. And, you know, so essentially it's a histogram that is colored by some threshold. So you can see whether this is, you know, high or low at a glance. So this is the KP index, and you can see here that, you know, we have this this big geomagnetic storm. We're in the recovery. There's some additional pops of activity there. This is going to give us a very enhanced radiation belt that's going to endure after this initial acceleration period. And so this is support for the fact that maybe that's contamination. So let's get back to our spectrogram. And so what we'll do, we'll set bin sizes explicitly. So we'll have a start time and end time. We'll set this to 1.5 hours. I'm using tick range again, but I want just the UTC times as date times back out of this. I'm going to set my bins for the y-axis, and these don't have to be even. So I can stack together bins with different resolutions and then pass everything through to spectrogram. So give this just a second. So what it's going to do is it's going to basically make this plot again, but with some explicit settings. Or at least it would if I had actually told it to plot. So what this has done, okay, I missed the plot on here. So yeah, so what the next thing is going to do, we're actually going to add data from other satellites to this. So we're going to loop over our satellites, read the data, convert the times, because remember this is GPS time. We're going to mask out bad data, and then we're going to use this add data to add this to our currently existing spectrogram object. And so this is just going to build up that map, averaging the input data within each cell, okay? And so here we go. So we've zoomed in some. I've got these custom tick labels that I've made. Everything is labeled now. And so you can see the flux. You can see that there's this kind of dark region here where essentially we fall down to negligible flux, and that happens at a different L value. And so this is essentially where those charged particles can't get because the magnetic field is shielding them out, okay? So we could do this at once instead of using add data. There's some sample code here. So that's kind of the data to get us to, essentially demonstrating that things are shielded, okay? What we're going to look at next is the cutoff rigidity. Rigidity is a momentum per unit charge with weird units because we're space physicists, not astrophysicists. So we'll use the IGRF module in order to evaluate this dipole moment. And so you can guess at this, but I'll tell you offhand, it is about 30,000 nanotesla, but it varies with time, okay? And so this is using the IGRF module, which underlies the magnetic coordinate systems. So we're also going to borrow some code that's in a different repository linked from the notebook, so that we can get the Stormer coefficient that we're aiming for here. And so this uses funky units. It uses the volumetric Earth radius in centimeters. It converts that to Gauss per cubic centimeter. And so then you get your coefficient from this. And so it's not using electron volts, it's using giga electron volts, it's using ab volts. So there's some funky units to keep track of. So next step in getting us to this varying dipole moment, we want to actually grab the dipole moment and then calculate that rigidity cutoff as a function of time. And I want to do this converting also between particle energy and rigidity. So for later inspection, let's look at this conversion between particle energy and rigidity. And so this basically builds a generic particle class with a rigidity calculation, and then also a calculation to build something from a rigidity so that you can get the energy. And so now that we have that abstract class, we can make one for protons. And so I'm doing this here. So now this is inheriting, and I can do this for any species that I want, okay? And so there it is, nice and simple, limited code, and I get to reuse that. So from a 0.5 gigavolt rigidity, we can say, well, this is 123 MeV proton. And just to check, if we convert it back, we get a 0.5 gigavolt back. So you can try this for different species, different charges. So the next step in making that figure, we need to get the magnetic moment as a function of time. IGRF 13 actually covers a wider range than Smart and Shea had in their paper, and they had to use multiple models to go back to 1900. So as is going to hopefully be smoother. And so what we're going to do is we're going to get an IGRF instantiated. We're going to make a time range. It's 508 times. And we'll just loop over them and get the moment of the centered dipole. So evaluating IGRF isn't necessarily that cheap, but what this is doing is looping over our epochs. It's reinitializing at every time, and then it's getting the magnetic moment from this moment attribute. Okay. So a cutoff at a given L will define this function here. Again, it's not really doing that much. It's just using this get Sturmer coefficient from above, and it's returning the cutoff at a particular L using a vertical approximation, because that's nice and easy. So now we have an array of cutoff rigidities. And that's going to give us all of the data that we really need for our final plot. So people often use either 15 or 14.5 in the literature without kind of, thinking too hard about it. So what do those correspond to? Let's mark those on the plot as well. I'm actually going to switch to one of SpacePy's other plot styles. Now I'm going to find where the 15 and the 14.5 sit. And then this is all just, as Dan was saying, this is all just tidying. Here I'm using our proton object to get the rigidity from our rigidity tick labels. And I'm going to convert them to energy to plot on a second axis. And so we have the rigidity over here. And so it's taking each of these values, converting them to energy, and then plotting those over here. Okay. So now we have reproduced roughly this. And this discontinuity here in the earlier times is because they had to use multiple models, whereas this is all just using IGRF. Okay. So what if you don't like this plot style? Let's undo it. And that will take us back to the Matplotlib defaults, or in fact, whatever you had applied before you applied that style. Okay. So, so the plot that we're making here now is we're just looking at for 3 different L values, plotting out the cutoff rigidity at that L. So it's just another presentation. And so we're doing exactly the same thing. You can see the vertical cutoff rigidity at high L is very much lower, and this then takes us into the realm of protons measured by GPS. And you can see here the very tasty Matplotlib defaults. Okay, we've got this data. Let's give it to a collaborator. Our collaborator wants a different format, HDF5. So we can write out to basically anything. And I got that here. I think everything is read only. So run this at your own peril. I don't know whether this will write to your personal space or not. It should. And so this is just making our data model object. And then, hey, let's see if this works. Okay, cool. So I should now have in my summer school directory, I guess. Actually, no, wherever that is. I should have, there you go, your unique file name here, .h5. And so that has now written this, this data that I just created back out to HDF5. You can write that to anything you like, read it back in. And yeah, so that's just kind of a little tour of how you might approach just a different problem that kind of gives a little tour of some of our capabilities. I'm going to stop sharing and kick this back to.
So Steve, there's one question in Slack regarding extracting the magnetic equator, which I will let you read.
Right. Okay. So currently, that's a good question. So currently, the IGRF module, it was recently added as part of the coordinates update, And so, as I said, it is a stripped down representation. So we use the full set of IGRF 13 coefficients. And for the coordinate transforms, we only need the first few coefficients to get the moment and the dipole axis. And so if that's centered dipole, that's the first 3. If that's eccentric dipole, that's like the first 6. So we do not currently evaluate the IGRF at arbitrary locations. So right now, that's going to be complicated, is the answer to that. And so I see here also a new question. Does SpacePy include particle tracing in IGRF or any of the SIG&NCO models? So I guess the answer to that is technically no. So we provide access to the SIG&NCO models, for example, through the URBM library. So we have an interface to the URBM library, which is an open source Fortran library. That doesn't explicitly have any kind of particle tracing. However, some of the example code that I stole for my last notebook came from a package called Shields PTM, and that is the Shields particle tracing module. And so that is a Fortran code with a Python pre-processing and post-processing package, which is where some of my code came from here. That will do particle tracing, and there's an example in there for how you would use that with empirical fields. So it's set up by default to use space weather modeling framework output fields. There's an example in there for obtaining IGRF, SIG&NCO, any kind of arbitrary field, and doing the tracing through that. So yeah, click through on the links. That's not, particle tracing is not a SpacePy feature right now.
Awesome. Thanks, Steve. And
No
also
worries.
Dan and John for your excellent presentation. Well, that concludes day 2. Thanks everyone for attending, all the excellent questions. And for those of you who are in person, we are going to have a buffet dinner provided by ESAC now. More to come from Arno on that.
Yeah, just go towards the canteen. That's right at the entrance, so you can't miss it. Thank you.